introduction. And today I'm going to be describing what we have done in the space of floor plan creation at Zillow. So let me give a little bit of a background first, because I think people who are outside the United States are less familiar with Zillow. Zillow Group is the leading real estate and rental marketplace in the United States. Just to give you a sense of scale, there are more than 135 million homes in the Zillow database back in 2021. I don't know what the most current number is, but that gives you the approximate number. And last year, the average unique monthly users are in the range of slightly more than 200 million. So we do get a lot of traffic, and this gives us a sense of the kind of data that we're dealing with at Zillow. Naji and I are both in the Rich Media Experiences, or RMX team, and the charter of the team is to create compelling home shopping experience for users. Three significant milestones are shown here. The first of which is what we call 3D home tours, but it is essentially, discrete panorama virtual tours, as you see on the bottom left. This is followed by interactive floor plans, where you have floor plans that you can sort of click nodes in the floor plans, and it will tell you, the panorama that is located there, or the photo that's located there. And earlier to this year, we shipped fixtures in floor plans. So now you can also see fixtures such as cabinets and toilets and faucets and fridges and so on and so forth. And Naji here can, you can talk to him later, because he led the team that shipped these two features. Let me now talk very briefly about the production pipeline. So we have photographers going to homes and capture a discrete set of panoramas. So because they're being paid to do this, time is money. They cannot afford to capture many, many panoramas. And so they are limited in, and we are limited in how many panoramas we have access to generate the floor plan. So we do have an interactive pipeline to do this that generates the initial floor plan, and then it gets refined, which is then shown in Zillow.com. And the top right actually shows you the result of localized media. By localized media, I mean you have not just panoramas, but also listing photos and fixtures, you can sort of see. So now, here's the interesting scenario. We have thousands of such floor plans, and we want to move forward to do more research. Well, what do we do? 3 years ago and 3 years ago, we looked at all the available data sets. The real data sets of issues with size, there's not many real data sets. That's a lot of homes, because we need the variation. Being part of the company, privacy concerns is very real. We can use synthetic, but there's a domain gap, right? But not only that, because it's synthetic, it's, the types of homes, the types of rooms that you generate is all manually constructed, manually designed, and it may not reflect the true distribution of homes. So we came out with the Zillow indoor data sets, and we released it 2 years ago. And it's been used a number of times. And we've been capitalizing on the data sets ever since. So let me just tell you about Zindi, as it's called. So it's based on non-furnished homes. That's number one. More than 1,500 real homes across 12 states and 20 cities in the US. More than 71K panoramas. And this reflects a tremendous amount of annotation work. As everyone knows, computer vision techniques do not always work. We cannot ship floor plans that are erroneous. And that's why we needed QA work to correct for it. And we actually put the corrected parts in Cindy. And this, at that time, is the largest real data set. We have annotated doors, windows, and openings. Now, openings is kind of interesting. It's peculiar to us. It is due to the fact that we're capturing very fast and discrete number of panoramas. In a small room, we usually have one panoramas. In a big room, we have more than one. If we have a room that's really long, the annotator would break up into multiple quote unquote rooms. And the partition is called the opening. So it's an artificial construct, but the union of the two panoramas will give you one big room. And of course, we have ceiling heights. The figure at the bottom right shows an example of an opening. The one that's the lines that are indicated in green are the openings. So this is what it looks like. Bunch of panoramas in Cindy. We do the room merging and we generated the 3D floor plan as well as the 2D floor plan. So all of these information is available in Cindy. A little bit of a definition. So we differentiate between the two types of panoramas, primary and secondary. And again, it's all about money, right? We don't want the annotators to look at all the panoramas. So we broke it into two parts. The primary panoramas are the ones that are used exclusively to generate the room shape. So if you have like 5 different panoramas, some of them are not very appropriate because they're so close to the wall and so forth. So they typically will pick the one in the middle to be used to generate the room shape. So that we call primary panoramas. The secondary ones are all the other panoramas. So what we do is we use a version of structure for motion to find the pose of the secondary panoramas relative to the primary panoramas. If you want more details, you can talk to Yu Guang, who's right over there. Can you raise a hand to let people know? Okay, great. Assumptions. We assume that for a given tour, the camera height is the same. This is the guideline that we give to photographers. So, and this is very important because if you don't do that, if they capture panoramas at all different heights, you won't be able to get shape. We have a panorama that's being captured that has a calibration pattern, it's the April tag on the floor. They capture it, and so from that they can compute the actual camera height, and from that you can get the actual shape of the room. It's not just based on scale; it's actual, feet and 4 meters. So we assume Atlanta world where the floors and ceilings are horizontal and we have vertical walls. That's it. It doesn't have to be Manhattan. So that's the Atlanta world assumption. The bottom right actually shows you examples of distribution. And this, unfortunately, because there's so many different photographers, it's not really uniform in terms of the sampling density. So at the top right, you can sort of see the annotated locations of, I guess, doors in yellow and the cyan for the window, and the boundaries indicate the boundary of the rooms at the floor and the ceiling. So you can actually render the Zindi at each floor plan in different ways. You have the floor plan, the location of the panoramas, wireframe, and 3D surfaces. So here are more examples of the annotated panoramas. Again, the yellow are the doors, and then you have the cyan as the windows. I don't remember what the color of the openings are, but I'm not sure if it's shown here. Okay, stats. I've talked about, Zindi having more than 1,500 homes, more than 7,100 panoramas. And if you break down the primary and secondary, they're about equal, with secondary having more, with more than 2,500 floor plans. But what is interesting is the different kind of distributions in terms of layout type. A lot of work make the assumption that the room shape is cuboid, but you can sort of see there are an appreciable number of them that are Manhattan and different kinds of shape, and a fair number that is non-Manhattan. For example, bay windows, which is definitely not Manhattan. And in terms of annotations, these are some of the numbers of room corners and number of windows it goes. This is also quite interesting. Not surprising that you have a lot of bedrooms and bathrooms, but what was surprising is that a lot of closets, lots and lots of closets. So you have to keep that in mind. Okay. So now that we have Zindi, we decided to cast the wide net. Okay, what can we do with Zillow indoor data set? This is not exhaustive. I'm just showing you some representative work that we did, including, layout estimation. Here we have, what happens if we have two panoramas that's only approximately known, but the poses are, and we compute jointly estimate the correct pose and the merged shape. How do we do floor plan reconstruction? How do we find the topology? In other words, if I were to tell you information about the panorama in terms of, say, room shape, room area size, the image, can you generate a bubble diagram that links rooms together? And there are two types. One is, visual connectivity. In other words, you can see one room from another room, or they're just connected through a wall. So we had interesting work on that. And there's also work done on post estimation where the panoramas are very far apart. How do we find that? That's not easy. And Naji and Enrique were part of this work on photo localization, which is really cool. And the problem that we were solving was, if we give you a 2D floor plan, and then the problem would be, how would you find the pose of a given panorama or a distinct photo? And this last piece of work, virtual staging, was collaboration with Carnegie Mellon University. So I'm not going to talk about all of them because there's no way I can do that. I'll just pick these two to highlight. So let me talk about the floor plan reconstruction from sparse panoramas. And again, the motivation is clear. We don't have dense panoramas, but we're interested in generating a floor plan. How do we do that? This work was done with John Lambert, who was our intern, and with his advisors. All of them are from Georgia Tech. We call it salve. There was some confusion whether we should pronounce it salve or salve, but I don't remember. Yuguan, what did we ended up pronouncing it as? Salve?
Yeah.
Okay. Okay, so this is pretty complicated. Ignore the stuff in gray. Just remember that the inputs are actually pairwise panoramas. And again, as I've said, we know the camera height. What we want is to generate a floor plan. Now, what we do is to say, we're going to start off with pairwise, compute the poses, and then put them all together to generate a global pose for everything. So this is a simplified version where we apply a known technique. I think we use HoHoNet for this to generate room layout. And then we make use of the known locations of the windows, doors, and openings to figure out hypothesis of where rooms can be joined. But that's not good enough. What we do then is to say, we have the room layout. Why don't we render the bird's eye view of the floor and the ceiling? And check to see if the parts that overlap are actually correct overlaps. And we train it to be able to tell us whether those are true overlaps or false overlaps. Once we have done that, then we put everything together in pose graph optimization framework to come up with a global pose, global camera poses from which we can reconstruct the floor plan. So it's actually pretty straightforward. So let me talk about the front end part. Okay, so this is what I just mentioned. Here's a simple example where we say, oh, these two doors, they might be the same door because they're kind of same width, similar width within a certain percentage. Let's try to join them, right? But we go beyond that. We say, oh, well, let's look at the bird's eye view for these two panoramas. We use HoHoNet to generate the shape. Once we know the shape, we can render the bird's eye view for the floor and the ceiling. It turns out that these two rooms are adjacent. You probably can't tell how they're connected. This is the door that connects these two rooms together. I hope you can sort of see what's going on. Right, they are the two columns of that represent the floor and ceiling are properly oriented, and you can sort of see now where they overlap, right? Then the question is, how do you verify it? Well, we use a network to do that. You might say, well, why don't you use traditional methods? Well, there are lots of matching techniques and so on. One of the biggest problem is illumination does change. From the time that you capture one room and then capture another room, the illumination may change. The exposure changes, the white balance changes. So there's a bunch of appearance changes that goes on that makes direct matching very challenging. There's also the issue of inexact correspondence. If the shape of the room is slightly off or is slightly kind of misaligned, then they won't have exact correspondence. So rather than trying to grapple with this directly, that was the reason why we opted for a deep learning-based technique. So to go back to our pipeline, we now have something to tell us, given a pair of panoramas, are they joined or not? What's the likelihood of them being joined? We will go to the back end where we will try to generate the global poses. So obviously, if you have all the relative poses, if there's absolutely no noise, it's easy to just chain them up. But life is not that easy. The way that we will compute global poses is we use pose graph optimization using GTSAM, which stands for Georgia Tech Smoothing and Mapping. And we use the Huber laws for robustness. Here's an example result. We have a bunch of panoramas and each panorama shape. And I'll just explain a little bit in a little bit to how to generate the final shape for each of the room. And that's in the middle. And on the right is the end result. What happens when you have come up with, the output of the post graph optimization, the merging of all the room shapes associated with all the panoramas. And that will give us the rough floor plan. So I'm not going to delve too deep into this, but the idea is, suppose you have multiple panoramas in a room, and each room is going to have slightly different shapes. But the interesting thing is the whole net will give you like some, confidence numbers. And what you do is you raycast, right? For every single panorama at each column, you get, okay, how confident I am that this position is there. And for each raycasted direction, we will pick the most confident one and take that as quote unquote the right answer, the union of the shapes, and that's what we have as the result. So more sample examples. As you can see, we can't get everything. And again, it's due to the fact that there's non-uniformity in how photographers capture. So we're dealing with real problems here. We cannot expect the photographers to do the right thing all the time. Sometimes they would capture one panorama that none of the panoramas actually see, or the visual overlap is very little. We have some numbers. We compare against OpenSFM and OpenMVG. And what I would like to point out is the localization percentage, the coverage. It's much higher than if you use traditional methods. But, as I've said, we are using the semantic information to try to align, so it's not as accurate as you can see. The translation error is higher. You can probably tell that depending on the number of panoramas, the more panoramas we have, the more computing expensive it is. It's combinatorial growth. You have issues with noisy annotations. As I've said earlier a couple of times, that photographers capture differently. And we definitely need visual overlap. But what is interesting is that Shabani et al., and this is Yasu Furukawa's group, they did some work on extreme SFM where they tried to kind of patch multiple images together, even though there's no visual overlap. And it's interesting work. You could imagine that this work complements what they did. Okay, so this is a fun project. Probably less fun for Tianchen and Bowie because they're the ones who's doing all the hard work. We just point them and say, code faster. That's basically it. So this work that appeared in SIGGRAPH, what happened? Oh, okay. So basically we have a single panorama and the goal is to do virtual staging. So here's an example where you have virtual staging. It was empty, you add furniture. You can edit also, and you can change the sunlight direction as well. So the basic idea is you start with an audio panorama, and you try to figure out which parts of it are specular and which parts of it due to sunlight. And once you have identified these two lighting phenomena, you try to remove them. And if you're able to remove them, you can add them back later on. So here's the pipeline. The thing I want to talk about most is the fact that we only use the semantic map to do most of the work. Because if you try to learn it, you need information on, you have the ground truth for specular reflection, you have the ground truth for direct sunlight. It's very, very difficult to do that from real data. And we do not want to rely on synthetic information. So what do? Well, we say, all right, we have a semantic map that tells us where the windows are, where the floor is, where the walls are. And based on where the walls and the floor are, we can basically figure out where the room shape is. And if you know where the windows are, we can basically say, you have this very bright region over here. What is the sunlight direction that's going to vote for the observation of the sunlight? So you're going to get information geometrically from that. We also, for specularity, we basically say, because of how reflection works, the location of where the specularity is has to be along the same column as where you see the window, right? And so that's why we use sort of a semi-supervised way of learning how to take out or identify specular reflection, because we kind of know where the area of specularities are. We can learn the appearance that's in that coarse mask, and everything else doesn't have specular reflection. And so we use that to train. And it's much easier than trying to manually annotate everything. It's going to be horrendous. So here is another example for furniture insertion. Yeah, it's pretty choppy, unfortunately. Yes, that's the idea. Okay, so we haven't solved everything. There are still challenges that remain. And of course, with the challenges, we have research opportunities. The first big thing is, as you can see, there are uneven data distributions, right? Room shapes, complexity of the room, et cetera. You have to be able to handle the imbalance. Can you do it effectively? Annotators are not perfect, and sometimes you get errors, and we fix them, but the fixing is not based on computer vision. And so it's non-optimal fixing. That kind of generates imperfect data, fortunately. Sparse panorama distribution, that's also the issue. Non-Manhattan shapes is another problem. Now, I mentioned ceilings, and I said the Zindi has ceiling heights. The problem is about 32.5% of all rooms have complex ceilings. By complex, we mean ceilings that are not horizontal. Some of them are sloped, some of them have different, weird shapes, and we don't handle those today. And of course, everyone knows it's variation of appearance. When you capture, you have, different white balance settings and exposure, etc. It makes it look very different. So that's it for me. Thank you. I'm happy to answer any questions. Yes.
Thank you for your great talk. How do you get the dimension? Do you guarantee sort of accuracy level for these floor plans?
How do we get the okay? So I mentioned earlier that we did the calibration where we put an April tag, and so when we capture and calibrate, we know the camera height. We know the camera height, and we know where the ceiling, the wall and floor meets. We kind of know the distance, and from there you get the dimensions. Does that make sense?
And do you have like an estimate what would be the error associated with that? And do you label the flow plans, or it just the annotation mentioned was from the panoramic images,
It's from the panoramic images.
no flow plan annotation?
Well, it is tied to the floor plan.
So you don't have the ground truth, I mean.
Yes, there's no ground truth. In other words, we don't get people to, take a laser and point and measure. Yeah, we don't have that kind of money.
One question.
Yes, just one. Yeah, thank you.
Thank you very much for the very interesting talk. And I have three questions related to the data set. Is it that publicly available?
Yes,
And what, it's like all the rooms are empty, right?
yes,
No furniture.
no furniture. That's correct.
And what is the resolution of the rooms?
Is it 1K by 2K? 4K? 2K by 4K.
Thank you very much.
You're welcome. Okay, thank you.
We have one more question in
Oh.
the chat. How did you do the furniture filling for panoramas? It's a very broad question. I think
So if we know the shape of the space, we can, well, it was kind of manually done. I'm not sure what it means. I think it's definitely manually done. We select the furniture ourselves. I believe. I don't know if there's any automation to ask Tianchen. But definitely it's quite direct. It's using 3D information. I'm not sure if I answered the question.
I'm not getting any follow-up questions here. Anyways, thanks, Singbing. Thank you
Okay,
so much.
thank you.
Stop sharing that. Thank you so much. All right, our next speaker is Huan Zhang, and he's an assistant professor at the National Taiwan University. Please join me in welcoming him. He's going to talk about understanding indoor spaces and all yours.
For the discussion and thanks for organizing the great workshop, and it's an honor to be here to speak. And so I changed the title of my talk, so it's different from the one on the program, and I think that new topic is more related to this workshop. So I will talk about understanding indoor living spaces from 360-degree panoramas. And so we will focus on the omnidirectional image inputs as the input. So it's represented in rectangular format. And why we are interested in 360-degree images. So apparently we can capture the global information in a single shot. And, so if we want to infer the global structure of the scene, then it will be very useful. And consider another way to capture the information from the surroundings. And you can have a limited FOV, and if you want to collect all the information, you need the wave sliding window to combine all the information, and then you get the global view. So if we compare the two different strategies to capture an indoor space, with the 360-degree panorama, we will have a relatively lower resolution because we squeeze all the information in a single image. But we don't need to worry about vegetation problem. With multiple images with smaller FOV, we can have a higher resolution, but we need to control the FOV, and also need to resolve the conflicts in the overlapping region. So the nature actually provides the two designs of the binocular visual systems. So for prey animals like pigeons, their eyes are on the opposite sides of the head, so they can have a wide FOV. So if there is danger, then it can quickly trigger alerts. But the drawback is the limited stereopsis. And for predatory animals like owls, they frontal their eyes are at the frontal directions, so the FOVs narrower, but they can have better depth sensing because from the disparity. But they also need a more dramatic way to rotate their head to collect all the information. So in evolution, we can only go one path. But when we are building a robot, we can have both systems on one robot and choose to turn on which one, and depends on the task. So I'll be presenting a series of projects done by my PhD students, and he is also co-advised by Min Sun. Min will present another project also done by Chen at the ScanNet workshop tomorrow. So you are welcome to join Min's talk. So I will talk about the three problems regarding geometric representations of indoor spaces. And if we consider the parameters that are needed for to describe the structures for the three problems, for a room layout estimation, we only need maybe 10 corners, positions of 10 corners. And for plane estimation, we need to predict the maybe 20 or 25 planes of the indoor scene. And each plane requires 3 parameters defining the surface normal. And for depth estimation, we need to predict the depth value at each pixel, so it's very dense. And we want to develop different methods for the different types of output. So for room layout estimation, we propose horizon net, and for plane estimation, we propose panel plane 360, and for depth estimation, we the whole nets. And all the methods are based on the assumption of gravity aligned fire. That for indoor space, we assume that the wall, all the walls are gravity aligned. And so for the input image, we need to make sure this assumption holds. And but that's easy to do the pre-processing. So we just take the line segments and then make all the vertical lines parallel to each other. So we can have a input image, input panorama that satisfies the gravity aligned assumption. So let's go to the first problem, room layout estimation. And the key idea of horizon net is 1D output representation. So we try to flatten the vertical, the height direction, to get a 1D horizontal representation for the room layout. So, and we also propose the other two tricks, panel stretch, data augmentation, and post-processing. And here's an example of 1D output representation. So when the horizon net predicts YC, the ceiling wall boundary, the position of the ceiling wall boundary, and YF, the floor wall boundary. And also need to predict the binary value YW, which indicates the, whether or not the column contains the corner. So the output will be 3 values at each column. And this is the architecture of the horizon net. So basically, we flatten the height dimension and then get a 1D representation. And we also use the LSTM to merge the information. And then after post-processing, we can get the layout. And the post-processing is based on the Manhattan word assumption. So we assume that the intersecting walls are perpendicular to each other. And based on the assumption, we can recover the occluded corner because we know that they are invisible walls. And we also proposed the panel stretch data augmentation, which is very useful for the improvement. And the idea is to, from the ground truth layout, we can stretch the layout in 3D, and then we reproject to the panorama. So we can generate a lot of new panoramas for training. And here are some results of horizon net. So simply using the 1D representation, horizon net can achieve very good performance, and with panel stretch and LSTM, the performance can be further improved. So we also, the results are on the earlier data set, but we also applied horizon net to Zend. And you can see that with post-processing, actually horizon net performs worse. So post-processing does not work, and it is expectable because Zend is based on Atlanta's word assumptions. So, but the post-processing is based on Manhattan assumption, word assumption. So it fails reasonably. And but if we skip post-processing, actually horizon net can perform quite well. And we can also observe some differences between Zend and also earlier data set that structured 3D. And one difference is the definition of layout, and also the because the structured 3D is synthetic, so there is a domain gap between the two data sets. So if we only train on a structured 3D, then we cannot perform well on zero data set. Yes. So let's go to the second problem, a plane estimation. And the problem is to predict the segments of the planes of horizontal planes and vertical planes, and also we need to predict the surface normal for each vertical planes. And all the results to be derived from a single RGB panorama. So if we take a vertical slice of from the panorama, and we connect the adjacent pixels to get the direction, and we will find that actually most of the pixels are on either horizontal or vertical planes. And also, we only need roughly 20 planes to cover 80% of pixels. So this is the property of indoor space. So we design a network to predict the planes, and it is so we divide the pipeline into two branches. One is for horizontal planes, and the other one for vertical planes, because the vertical planes need additional information like surface normal and also the planar depth. And so we from the backbone, the ResNet backbone, we predict different parameters, and then we can apply the clustering to merge the similar pixels into planes. And with the planar depth and also pixel embedding, we can compute the loss function based on the geometric consistency. So our method can perform quite well, and compared to previous methods, you can see that based on the planes are more consistent. And so let's move on to the third problem, depth prediction. And we propose the HoHoNet for this task. And actually, HoHoNet can be applied to different tasks, not only depth estimation. And the main idea is to extract the so-called LH feeds, latent horizontal feature. So from the latent horizontal feature, we can use the feature to for different tasks, including room layout estimation, and semantic estimation, also the depth estimation. So we use a ResNet backbone again, and then with the efficient height compression block, we can get the 1D representation. And instead of using LSTM, we use multi-head self-attention to combine the information, and then we get the 1D feature, LH feed. And then from the 1D feature, we can predict coefficient for inverse DCT, and the coefficients with the inverse DCT basis, we can we can multiply them and then get recover the entire column of the depth. And HoHoNet can achieve quite good result on depth prediction on different data sets, and also the visual quality. The visual quality is quite good, and it can, as I mentioned, it can be applied to semantic estimation and also for room layout estimation. And compared with HorizonNet, the HoHoNet is much faster and also more accurate. And I want to mention two related projects. The first one is called OmniNerve, which can be built upon the depth estimation results of a whole net. So the idea is the problem is to create parallax panorama from a single panorama. Because with a single panorama, we can only have a surrounding view from a fixed center. And if we want to move to another position and to generate this virtual panorama, then we can create the parallax effect. So here is an example. The red dot is the position of the camera, and we move the camera along the green line. So at each position, we can generate a new panorama. So we call it omni-nerve for the name omnidirectional neural radiance field. So it's based on a nerve. But the problem is easier here because we only have rays casting from the same center. And so the problem is that if we have one panorama and also the estimated depth map, and we can change the camera position to a new position, and we project the so based on the depth information, can we project pixels to the new panorama, but we will have missing pixels. So the green pixels are missing pixels because they are unseen from the new position. So the problem is, can we train the MLP to learn from the seen pixels and to predict the unseen pixels? So this way we can generate a new panorama at new position. And compared to direct interpolation to implant the missing pixels, the omni-nerve can preserve better the structure. And here are the results to move the camera. So the input is a single panorama that we can generate new panoramas. So this one is from medical data set. Created a parallax effect, although we only have one input panorama. Also from medical data set. The other project I want to mention is self-supervised 360 room layout estimation. And so we assume that each room is captured from more than one viewpoint with a constant distance to the floor and known relative poses. So actually, zero indoor data set provides this kind of data that we can test our method. So we apply all the tricks we know for in room layout estimation, and also from the previous project, omni-nerve. And so we try to train the horizon net without the ground truth annotation. And we only have multiple, so two panoramas as inputs, and then without the ground truth annotation. And so based on the loss functions to that based on the loss function that that take care of the all the consistency, like panel stretch consistency or the layout consistency, and also the photometric consistency. We can predict the layout without the ground truth annotation. So the training is the only the training data from the training data. We only need the multiple panoramas taken at different positions in the room. And the green lines are the predicted layout, and the red lines are the ground truth. So we find that with the self-retrained horizon net, you can outperform the ImageNet pre-trained horizon net. And also it provides an interesting application that for active data selection. We want to know where to take the next panorama that can reduce most the uncertainty. Then we can use the consistency, the loss function as the indicator for the uncertainty, and then we can find the next location that most suitable for to take the panorama and can reduce the uncertainty. To conclude, so we have talked about how to learn effective geometric representations for different tasks like room layout estimation, plane estimation, and also depth prediction. And all the methods are based on utilizing better the properties of indoor living spaces. Thank you.
Questions?
Very interesting talk. How do you deal with uncertainties in panoramic images? Consider that you have like cell phone generated panoramic images. How do you think the robust approach would be? Have you tried that methodology before?
You mean that this test?
Yes.
Okay, so when we train the horizon net without the ground truth annotation, we can include all the consistency loss. For example, for the photometric consistency, we can move the source camera to the virtual position as the target camera, and then we render the target view from the source in source panorama, and then we can compare the rendered one with the real target one. But we will have the issue that lighting changes, as mentioned by something. So, but we with some robust estimation, we can include all only the reliable pixels into the photometric consistency loss, and also we can estimate the layout using the horizon net, untrained horizon net, and then from the layout we compare the predicted one with the target one. So we can have a layout loss, layout consistency, and we can also apply other prior like Manhattan line or ceiling for consistency, and all these consistency losses provides how good the horizon net performs for predicting the layout. And so if And we can pick different positions in the room and apply the same pipeline. And for those positions that have large consistence loads, we know that if we take a new parameter at that position, then it will useful to improve the performance of resonate, and that gives us a hint for the uncertainty. It's the main idea.
I have a question. So for, you have a target and a source panorama. Did you use any priors for selecting the target? Is that the one that's probably in the middle of the room, or you just randomly pick any panorama can be a target?
Yeah, in this for training, we pick it randomly.
Great. Does Tiger speak here? Uh, 15 minutes break, then we'll be back at 8. You know much?
Yeah, use it. And we give us feedback, but let us know what we're doing.
Hi, how's it going?
Some aspects.
Najee, nice to meet you.
Yes, just a question, general, for this workshop in general, are the presentations available, the PowerPoints or the papers or somewhere?
So it's being recorded, so we're gonna put up the recording on our website. And it's up to our presenters if they want to share their slides. I will ask and see if they let us. Share them. But yeah,
Let's recording.
recording will be available. Yes.
Yeah.
Yeah.
That's very good. Very nice so far.
Yeah, thank you. Hey, Enrique, how's it going?
Did I just say hi?
See you.
One recommendation, maybe you can remove them.
I just did. Yeah. Is,
Okay, yeah.
is that how I should do it? Like the, yes, I think
Yeah,
someone just
yeah,
joined. Yeah. I had no idea. Thanks. How's everything? How's Min doing?
He's doing pretty good.
Yeah?
He was offended like 10 days ago or
Really?
14 days ago. Yeah.
Nice, nice.
Yeah.
Is he staying in academia or?
No, I think he found profitable opportunities.
Of course, I'm sure.
Elsewhere. No. Actually, he was really torn about it. About whether to procure a postdoc and then go and build a academic career or as I told him, take the money and run.
It's a tough call to make.
Yeah. No, and I think
He definitely had the talent.
Yeah. No,
Either way.
Yeah. I was thinking that he was in his mindset. He was kind of like, oh, the job market is really not that good now. So it probably is a neutral move to go to academia because just kind of like postpone. Sorry, go to a postdoc.
Yeah.
He will.
Not for him. He's a top performer. I think that he could always find opportunities.
No, and he did. I think he's going to Apple.
Nice.
So,
Do you know which team?
no.
Hey, Thomas, how's it going?
How are you?
Good.
Good, thanks for the invite.
Of course.
Yeah.
Thanks for accepting it.
Hey, nice to meet you, Enrique. Yeah.
You know Thomas, right?
Yeah.
Yeah, so I got my laptop here. I'm gonna probably start setting up in like 3 minutes before.
Should be perfectly fine now. I'll just ask you to just use your own laptop, join the meeting.
Okay, you
Because
wanna
like
join?
everything is set up here with audio and video. Just join the meeting. Hey, Anna, how's it going?
Okay, sounds good.
And then just share your slides. Just make sure when you're joining, your speaker and mic are off. That's it. It's up
My
to you.
speaker and Mike, I'm gonna be using this mic here.
Yeah, so everything is set up to record the audio and video, the audio. So speaker and mic off. It's up to you if you want to turn your camera on or off.
And giving my laptop. can be
Yeah,
here.
you don't need to connect anything to it. Just join the Zoom link. It's in the email that I shared.
Okay,
Yeah.
that sounds good. Okay, I'll start.
All right, cool. How's it going?
Now I probably need to repeat the instructions, so I'll just join the Zoom link and share this.
Yeah, it's just
And
like
then
any virtual room.
Okay.
Yeah.
And then what's being, where is the video? or-
So you can turn on the video on your laptop
I
if you
see.
prefer to.
Yeah.
Just make sure that you keep the speaker and the mic muted. Yeah,
Okay.
everything. Yeah. How's everything?
Sorry for being such a delinquent responder to emails.
Oh, don't worry.
I have had the worst semester.
That's thing.
I hope it's the worst. I-
Yeah, yeah,
it's not good. So I have been constantly in this mode, like, like 50 emails, and then if it like goes below the visibility. then
Yes,
I-
yes.
Yeah.
I was like, I need to do that, something I got interrupted. but
I just made the assumption that everyone's reading and if they have
Yeah.
questions, they're gonna respond.
Yes,
Otherwise,
yeah.
everything's fine.
Good
Oh.
assumption, especially for this overwhelmed faculty.
Oh, yeah.
How are you?
I'm pretty happy. Yes, because semester's over.
Yeah.
Yeah, oh, CVPR is always got time for me. Because I don't have to.
Sparks a lot of,
Yeah.
yeah, the beginning of summer more or less.
Yeah, the weather's getting good and the students are in the back mirror now.
Yeah.
Nice.
You don't have to read and edit papers anymore.
Oh, yeah, I guess I will. No, I mean, at this point also CCV is done, so it's just smooth sailing.
Yeah.
Going forward, or that's what I told myself at this point. And let's see how it goes. Yes. No, it's really nice, this location. I never been to.
Oh, yeah.
Yeah, I brought my kids.
Nice, yeah, Vancouver is pretty nice, actually.
Yeah, no, they always take a lot.
Yeah.
The CVPR is the family trip.
Yes.
Because it's typically,
Well,
yeah,
I mean, it's like they don't have a choice, right? It's like, okay, we bring the family to.
I've been running this racket for a couple of years now. That's okay. But, the one in Las Vegas was a little bit questionable.
Yeah.
It wasn't very kid friendly. But we made it work somehow.
Yeah, it's a good time of the year.
Summer school is out.
Yeah, school was out. Yeah.
I'm gonna find the email and.
Yeah. Actually, I gotta give a talk in another
Okay, yeah, cool.
concurrently, so
Yeah.
I'll leave you here too.
Yeah, thanks for showing up. Appreciate it.
No, I want to come say hi in person.
Yeah, of course.
Enough of.
Send us your good students.
Yeah, well, yeah. Well, means gonna be hard to beat.
Oh,
Yeah.
yeah, definitely. That's,
Yeah.
yeah.
Yeah, I think maybe I'll send better behavior.
Fine. It's a learning curve for all of us.
Yeah, we.
All good.
I'll just run to the restroom and then.
Okay, sounds good. Should get a coffee or something afterwards.
Yeah,
I don't know how your schedule is. I'm gonna email you.
Sounds great. You know,
Maybe.
You probably won't remember me, but I can name you. Oh, but that's a big city. Charles Stewart's. Treating me like just to you would be so first. Large science came to us. You're just gonna. Right now, that's my. Suspension on it. That's the first thing I'll be like. Yeah, but it's an inspiration for you in your private stage like this. Decades later, you might be like also. It takes a career, you know, you gotta get there.
That's why I know that you look familiar. It's just that I mean, I know your name. But it's just that.
Yeah, so that was my first.
How's he doing, by the way?
He was doing some kind of animal trafficking in Africa a couple of years back. I know he was always making like chain maker for like the young kids to get. I haven't seen him in the last 2 years, but it's still nice always to go to.
He still has to retire.
I don't think he has, but yeah, at that point, he might be without it.
Really nice guy. I agree with that.
Yeah, I still made that place a home for himself.
Well, I'm really looking forward to it.
Sounds good. I'm gonna go in a few minutes.
Yeah, so my team is mostly scientists, but I'm doing some science publication, some product. Otherwise, we're not gonna get the money. But it's very science heavy. I could see that I lead very science heavy, but the research that we're doing is also has some couple of projects and the singing mentioned. Yeah, we kind of everything. I'm a very. Make sure that the public warrant is papers. Students interested in doing internships or something. Yeah. So. You're going to see it. That's all. Yeah, that was a. All right, welcome back. We're gonna start another round of presentation. Next one is Thomas is gonna do that. He's a research science manager at Meta. I don't think he needs any introduction. We have you in the field, know him for super glue. So with that, let's move on to it.
All right. Thanks so much for the introduction. So first of all, it's a great honor to be here. I'm going to tell you guys a little personal story of why I think it's a great honor for me. In fact, one of the first great researchers I ever met was Dr. Singh Bing Kang when I was an undergraduate at Rensselaer Polytechnic Institute with Chuck Stewart. I was an undergraduate. He gave me a desk, a computer, treated me just like a PhD student. So Singh Bing probably didn't even know I was an undergrad, not yet, officially on the doctorate track or anything like that. It's a great honor to some 20 years later to be basically on the same stage as somebody that I kind of like looked up to. The basic lesson there is that if you're, no matter how small you are, if you're kind of in the crowd, you just sort of like fight for it, do good work, and who knows, in like the next chapter of your life, you'll be alongside that person you sort of idolized. So really, it's a great honor to be here. Title of my talk today is Deep Learning for Indoor and Outdoor Mapping via Egocentric Wearables. I brought a couple of specimens of my favorite kind of egocentric wearables here. I'm going to talk about two deep learning techniques. One of them is superglue, which many of you know about. I'm going to not talk at great length about that. And then we'll talk about something new coming out at this CVPR called OrienterNet. For egocentric wearables, let me start off with a quote that I saw in my high school classroom 20 years ago. This was an exercise to get students thinking about a quote and writing essays. The quote goes as follows: "The window through which we peer circumscribes the world we see." As a high school student, I probably wrote about language and my capability to speak Polish and English, and how having two different languages in my brain allows me to communicate differently. Certain things are better represented in English, certain things are better in Polish. That gave me a kind of mindset there. Now 20 years have passed, and I've been obsessed with computer vision. That's my life, my hobby, my life sort of work. And in this case, the window, it's the sensor, the device that you use to point at the world. And that gives you very different feeling for your work. I have with me two of my favorite windows. My first favorite window is the webcam. Simple. USB plugs into a computer, run your OpenCV script, point the camera around at the world, start looking at heat maps, start debugging it. Oh, it works well there. Move your laptop, go somewhere else, keep the camera plugged in. It's a little bit cumbersome, but extremely lightweight. This idea of having a camera in your hand, dog fooding your own creation, running on a new corner. Oh, your garage is kind of dark. You want to see if your algorithm works in a dark place. Go to your garage, bring your webcam, check it out, see what it does. That kind of thinking resulted in a certain mindset, a certain set of activities that we were doing for many years. And the culmination of that is superglue. And I just saw Paul sort of enter here. So he's the individual I'm going to be mentioning. He was the first author doing this. He did this as an intern in our group as part of his master's thesis. Superglue is a graph neural net and an optimal transport layer. The goal of this network is to create sparse correspondences between a pair of images. It's something we designed to work real time with a modern GPU. And I still recommend everybody go to the website, download the code. It's going to work on a webcam, the default demo. It's going to work a little slower if you don't have a GPU, but it's really a great way to just get a sense of this is going to be good for my application or not. Now, years have passed, and now I can tell people like it. They're using the technique. They're comparing against it. Now there's probably 1,000 reasons why you should use it, not just like we packaged it in a simple demo. But this is a great network, worked really well for us. And just to give you a taste of what this means is if you just use deep local features and some matching heuristics, you see results on the left. Green lines are correct correspondences, red ones are incorrect ones. Notice the bathroom floor, those tiles locally are very ambiguous. You don't get a high percentage of correct matches, but when you use the superglue matching network on top of those super point features, you get a significant higher set of correct matches. We submitted superglue as a network to many different challenges. It did quite well on indoor and outdoor things. I think the result of it working well on many different applications stems from this activity of use the webcam and be daily deploying your network on interesting parts of the world. That's been something that doesn't get the quantitative number, but it's a mindset, it's a philosophy. So all the researchers who worked on this, we were running this network and looking at interesting nooks and crannies. It's working here, it's not working there, building our own neurons around those responding heat maps. So that's something I highly endorse. The webcam really made it possible. Let me now talk about Orienternet. This is another one of Paul's lead projects, which is going to be discussed this Thursday at the evening poster session. Full title is Orienternet Visual Localization in 2D Public Maps with Neural Matching. There's a big team of contributors. This was a Meta AI internship that Paul had done. So there are a lot of different brains you can tap into now, as well as other devices that he hasn't been using before. So what motivates Orienternet? Well, it's this basic idea that a human can go to a place like Disney World. You can be given a 2D cartoony map that looks like it's designed for kids that says, here's a little picture of a castle, here's a garden on the right, here are roses there, there's a hot dog stand. You can show up in Disney World, look around saying, well, I see a hot dog stand and I see roses. You look at the map, you look at the world again, and you're like, oh, I must be here, and Magic Kingdom must be that way. So how do we design deep nets that can work like that using those maps that don't have sparse points inside of them? Well, the input to Orienternet is an image taken from a smartphone, some wearable device, and anything. This is a calibrated image. We know the intrinsics. In this problem, we don't care whether we're looking up or we're sort of looking down. We care about the 3-dot localization, the XY location in the world, and your theta, your orientation. So Orienternet is going to take a map. Here it's taking an OpenStreetMap. We use a GPS prior, so we have a hint. We're like, okay, we're roughly around these few blocks. Usually human knows sort of that too, where you are. And then we consume this map as well as the input image. Here, the map is coming from OpenStreetMap. You can get that for lots of different parts of the world. Orienternet performs neural map matching. It takes that 2D image, converts it to a neural bird's eye view representation. And it takes that OpenStreetMap tile kind of 2D map and also converts it to the same neural representation. And then it's trying to kind of basically correlate those features to localize where you are in the map, and you get resulting heat map. You can also integrate GPS priors. Any other localization system can give you a prior. You can integrate that fairly easily as well. Again, on those OpenStreetMaps, you will have things like gardens indicated, crosswalks, buildings. It's not going to have things like SIP features on this part of the building. That's not OpenStreetMap. It's very much like a kind of a Google map you're looking at. Probably most of you are looking at those maps this week to navigate Vancouver. It's your first time here, which is true for most people. So this same network, this oriented net, shows zero-shot generalization. We show examples from Aria glasses, that's a Meta AI wearable unit, also from mapillary data that's collected from smartphones, as well as kid autonomous data. What you see on the bottom is there is the recovered orientation, and I know it's very close to the ground truths. If you don't look carefully, you'll just see the black dot. You won't see there's a red line below it, but you'll see the GPS localization is in blue. So in a lot of these results, the GPS thinks you're on the other side of the street. That could be quite catastrophic if you're like, I have to get to this room by this time to give my talk. You can't be on the wrong sides of the streets getting lost kind of around here. And now you see kind of overlaid some of the heat maps. So the heat maps gives you a response to where you think you are. So take a look at the bottom images. They're going to very quickly convert into heat maps. So these heat maps whose peaks are the localization of where you are in the world. Here's some more examples of AR data from the Aria glasses. The top row shows the result in Seattle. The bottom shows a result in Detroit. You are seeing, again, when you look carefully at the second column, you'll see the blue dot is going to be a GPS only localization, kind of on the wrong side of the street, and we get the correct location. I mean, might not be correct within the level of you're playing Pokemon Go and it needs to be rendered kind of within centimeters or meters, but you are kind of getting, I think meters is good enough sort of level here. And you can see on the way on the right, kind of zoomed into some of those peaks kind of around the heat map. That's where the central hotspot is, the ultimate localization. Now, we've also been able to apply oriented net to a sequence of images. So very rarely do you have just one image. So what if you have a sequence of images and you know the relative poses between those images, but you want to localize yourself on a map? So here are 3 images extracted from a sequence. And on the bottom is that heat map response to what happens if you do per frame localization. They're kind of noisy. There is a peak in there that you sort of see it, but you see there's some kind of confusion there. So if you integrate or if you use the successive predictions, let's take a look at the updated heat maps. So the first one's still the same because you only have 1 frame. That one didn't change. I'm going to kind of just go back and forth a little bit. Let me go back. These are the noisy heat maps. And I'm going to click forward once. And now you're seeing over time, the heat maps get more peaky. This is kind of an expected result, but it's a nice property of a system to say it works in per frame scenario, works on sequences, works with your priors obtained by just about any other system. And here's what the error in localization looks like. The green line is GPS that we're seeing. It does an okay job throughout the entire sequence, not necessarily getting better over time. GPS isn't really using your last location. Then if you do the single or the per frame oriented net localization, you see most of the time it's better than GPS. There are scenarios where you might be looking at a particular tough shot where GPS does better. But the red line, which is the sequence, which is the fusing of successive predictions, that gives you a better result and the error tends down the expected behavior. So now for this part, I'm going to talk about Project Aria and indoor modeling. So I brought my Project Aria glasses. These are the ones that I use at work. I'm not going to turn them on sort of for you, but they're glasses that if I walk around, people are like, oh, you're wearing something. But it doesn't block my view, freeze my hands. I can now do research by doing the stuff that I wanted to do. In the earlier world, I was holding up a laptop in one hand and the webcam in the other, and then venturing into nooks and crannies of my home and my house to deploy sort of the model. But it was changing what I was doing. One hand holding a laptop, one hand holding a webcam, or tied to a desktop and saying, I'm only going as far as my cable will reach. Now, the window has been enlarged dramatically. Now I put it on, hit my record button, and I go off and do whatever I want. I can climb things. I can try to ride my bicycle, not necessarily recommended on a street because it does block a little bit of your periphery, but in the webcam world, I could have never used both of my hands to do something the organic way. I can cook, I can clean, I can play, I can do whatever I want. So that's that window that ARIA has created for me in my research life. Now, the ARIA synthetic environments, that's something I think is quite relevant to this workshop. That's what I wanted to talk about and mention it. This is 100,000 unique scenes that are procedurally generated. Each scene is filled with high quality objects coming from a digital library. And most importantly, trajectories are simulated within the environment to simulate how a human would walk through this space. And all the sensor specs and how the images are created are meant to mirror this device. So by consuming this data set, by downloading it, by bringing it into your research life, you can experiment with lots of diversity, not be worried about recording scenarios of I had to get permission to record in these rooms and these not, there's bystanders or not. There are no people in these environments. You're not going to be worried about which of these frames do I show, which ones do I don't, because they're procedurally generated, because it's synthetic data. Now, as well as the data, we packaged together a lot of tools that make it easy to get up and running with this data. Python visualization tools, a whole kind of ecosystem. And I shared a link here, and I'm going to share these slides later, but this is going to be discussed in great detail tomorrow. We have an ARIA theme tutorial, which is all about ARIA. Lots more stuff that I'm even touching about. It's going to be all about what you can do with an ARIA, how academics can get ARIA, and talk about projects that are already using it. There's a lot of support from Meta to get this kind of device. Again, this is not something yet for moms and grandmas of the world to talk to their kids. It's a research device for collecting data. It's like the webcam I used in my example of holding it and trying to see what happens. You want to know what happens if I wear gloves while I do this activity or that? Okay, you just put it on, record again. It opens up lots of scenarios. So I encourage everybody to come to the tutorial or just check out the website and read about a subset about ARIA. But this, we are basically wanting to create more and more interactions between academic researchers, their problems, and what we care about at Meta, which we care about, egocentric activities, and we care about not so much playing just a game in one corner of the world. We want you to go hike up and down mountains, do fun, adventurous things, and have a sense for AI to help you out. So let me summarize what I talked about here. I talked about this kind of example of a window, and I really talked about a webcam and the ARIA glasses. For you, window might have a slightly different interpretation, but choose that window wisely. It's going to either open up your creativity or limit your world based on how you peer into the real world. Then deep learning for localization, Superglue and Orienternet, it seems to deliver. There's lots of different ways to cast the localization problem, whether you're doing sparse, dense, direct. I think there's still fun and exciting ways that deep learning is going to be used for localization over the next few years. So I think looking forward to those fun and creative uses, that's what I look forward to, not just refining a worldview that we know about. I look forward to learning from each of you and all the CVPR participants how they're using different kinds of deep nets. And finally, Project ARIA glasses allow you to do daily activities. The stuff you do every day without thinking about it. You can record that data, you can then analyze it however you want. We have a lot of tools or even data sets to get started with this kind of data. No cables, no hands, means you really are free to do what you want. And finally, to learn more about the things I talked about in this talk, you can find Paul and myself at the Orienternet poster session happening this Thursday in the evening. Come tomorrow or check out just the website links about the Project ARIA tutorial that's happening tomorrow in the afternoon session. If you see anybody walking around with a shirt that says ARIA and has a logo like this on the back, you can just tap on their shoulder and say, tell me everything about ARIA that I need to know. And they will warmly greet you and say, tell me about yourself, what you want to know. So there should be plenty of us walking around. And with that, I'm going to conclude my talk and take a couple of questions and give you guys answers. So thanks for your time. Meet your question. Hi.
So my question would be about the licenses on the area dataset and everything. And before you answer, I would also say that Superglue was a winning part of winning solution, not only 2020, but 21, 22, and now 23. So like it's really amazing job. But my question is about the licenses and everything. Can we just download and use it, or some paperwork?
You're talking about using the data sets that we've released as part of kind of Project Aria. So for using the data sets, we've gone through great care to make sure if there's anything involving the real world as anonymizations, we're very selective. That's why I was promoting the synthetic data sets, which don't have this concern about real people's environments. Using the data sets is much, much easier than getting your ARIA. Getting the ARIA, it means people have to agree and read rules. What happens is, they're basically rules about being a good citizen. We want to discourage people recording in places where they shouldn't be recording, be kind of a good guy. Don't use it in a way that's going to annoy anyone else. I know there's already rules like don't use phone cameras in locker rooms and things like that, but we're very worried kind of about the use. So the university has to agree that, yeah, there are rules about kind of using it, but once you get Project Aria as a part of your research team, you collect your data, it's yours. You do whatever you want with it. We don't want it. It's yours. And all those details are actually explained. And if you have specific questions, there's a lot of people who know a lot more for those sort of specific answers. But there's a lot of us here to help you figure out which part of this ecosystem you want to use and which one you still want to wait. Okay, another question?
Do you have the depth data also generated by the ARIA class?
So there is no depth sensor on the device. No.
Do you have plans to add time-of-flight sensor or LiDAR scanner? So that's needed for localization, like accurate localization.
Yeah, again, well, I'm going to tell you that there are two SLAM cameras. There's a left and a right SLAM camera. There's an RGB camera in there.
Yes, there you go.
Yeah. We have an ecosystem of machine perception services that, given this data, you send it to me and we can run the localization stack, get you all the high quality results out without you worrying about it. The localization algorithms aren't sort of open source that we use on top, but we get really good localization. As a part of also the tools, you get the ability to create semi-dense point clouds. It's not quite like that per pixel in full glory, but with really stellar localization come pretty good sparse point clouds. So to see examples of those, you can kind of go online and see what they look like, but that is something that you can kind of easily obtain. So hopefully it gives you half satisfaction.
So have you done any like benchmarking how accurate these point clouds are? Yeah, they're dense, but in terms of the scale, how accurate they are?
What do you mean in terms of the scale?
Measurement. We don't know that one. Like the, I can ask like.
Yeah, we can offline chat more about that.
Hi, my question was about for the internet. One can imagine if we are not looking at the scene in the right way, not enough context, perhaps in the scene. Like, how do you deal with that? Like, is there some kind of like implicit depth estimation or something to know whether you are looking at you're not covering a large amount of the scene enough to localize yourself?
I think with almost all localization techniques, they're going to be blind spots. I think if you're walking around, for example, this room, and you're just looking at really a wall here, you're not going to be able to localize yourself. If you're walking around the street and you walk by a corner and you like look away for a few moments, there are going to be blind spots there. I think any system that works on per frame, you expect to have blind spots. Even earlier, I showed that Internet sometimes can do worse than GPS sometimes. But when you do the fusion of the successive measurements, that problem tends to go away.
Okay, yeah.
Thanks, Orientina. The rules quite great, but what kind of data do you actually extract from the maps? How do you convert it to quantitative data? For example, you mentioned there's a tree, there's a park.
So that's basically the magic that kind of happens behind the scenes. I'm going to just jump to one of these to result here. There is no, we're not explicitly designing kind of what the features look like. There's a little bit of like, this representation emerges from the large scale learning that we do. So we anticipated something like this to happen, but we didn't even really know before how well this would work. In that sense, there are more details in the paper, but Paul is in the room. We can even talk in a little bit more depth after the next talk during the break to try to pinpoint to the sections of the paper that are going to give you the answers that you're looking for.
Okay, thank you.
Cool. All right. Well, thank you, everyone.
Thank you so much, Thomas. Trying to get set up. Right, our next speaker is Anna. Anna is the professor at George Mason University. I had the honor of collaborating with her and a couple of her students as part of our intern project. And she's going to talk about your understanding for us.
Give me a second. I have just to straighten out the. All right. Well, thank you for inviting me. It's sort of exciting to see some old friends and new friends. And so, I've done a lot of work in reconstruction and mapping, and it's exciting to see how the field advanced and how we can do localization and mapping either from single view or panoramas. And so I'm going to talk a little bit about how to endow some of these models by semantic information, because this is something we have been interested in sort of past years, and what are the challenges of using the state-of-the-art techniques to do so. And then I'll talk a little bit about sort of navigation and exploration strategies. So this is a problem which is very dear to roboticists, but I hope thinking about it and sort of discussing a little bit what are the type of techniques we have at our disposals and how learning can be used. Maybe you will sort of find it interesting also for some of your applications. So in majority of the talks we've heard so far, the final goal was trying to build the 3D model of the environment, right? And we have seen a lot of variations of this. So the next step, which you can imagine could be quite useful, to actually endow this environment with semantic information, because semantic information sort of provides this also nice interface between natural language, and currently you have sort of a lot of interesting applications which are arising where these two areas are becoming closer and closer together. So the first part of my talk, I'm going to talk about semantic mapping and what it takes to actually endow these models with semantic information. And then typically once you have the model, you are interested in actually doing some activities autonomously in the environment. So this is of great interest to roboticists. And so if you have a high quality 3D model, then you can do path planning, control, you can do search, you can do fetch and delivery. So there is a big subfield of service robotics where these are the type of things people are interested in. And so I'll talk about a little bit about this. So here's sort of an example of what it means to endowing the model with semantic information. So this is a very classical problem of semantic segmentation in computer vision. And the majority of the settings, you take a single image, you train a model where you require large amounts of pixel level annotations in order to predict labels of individual categories. And so we have some example of indoors environment, and then you can sort of understand where you have walls, tables, obstacles, small, big chairs, and so forth. And of course, right now, the state of the art can sort of handle probably up to maybe 10 or 20 or 30 categories, but you can imagine that doesn't really extend well to the wealth of the information we typically see in indoor scenes, which are the examples you see at the bottom, right? And so in the context of robotics applications, you would really like to be able to segment anything and name anything. And this could be also a potential interest for other kinds of settings. So suppose that you want to have some assistance systems where you're looking for things, right? And you would like to be able to have some way how to provide guidance to the user where things might be. So even if you take the autonomy part out of the equation. And so, as I mentioned, there is this, with the emergence of this learning and deep learning and some sort of uniformity in the architectures, which are emerging in these different sub-areas, there are really these nice synergies between self-supervised learning, vision and language models, where language and semantics mean, and then also decision-making and language, where you can imagine you have these abilities to actually give instructions in natural language. And we have been sort of thinking quite a bit in navigation instructions, but this could also be instructions in doing certain kinds of activities, which could be also relevant for augmented reality setting. So this is just to kind of position a little bit into the broader class of problems we have been thinking about. So classical semantic segmentation, you take the state-of-the-art architecture, pre-train on sort of pixel level labeling data set. And now imagine you want to deploy it outside of this in a different setting in your particular environment. So if you take it, you run it, things are going to perform very poorly, because almost every realistic environment is quite likely have some portion of it which is going to be out of distribution. Okay. So then if you would like to have a really high accuracy in a setting like this, you have a couple options. You can either go and label the components which do not perform well and fine-tune the model, or the other sort of avenue which we sort of try to explore is, instead of trying to learn these general models, which try to generalize to arbitrary environment and fine-tuning them, we wanted to explore the avenue of actually learning the models for specific environment. And so this is the setup. I have a video, and I have an opportunity to move around in the environment, and I would like to have a mechanism where the model which is being learned for semantics is particular to this environment. So I do not particularly care whether it generalizes to other couches or other tables, but I would like to be able to describe and name everything in this environment. And so naturally, in order to avoid this challenge of requiring large amounts of labels, which there are order of 10,000s, and pixel level labeling is very challenging, as you can imagine, for the semantic segmentation, we sort of started looking at these ideas which were around in self-supervised learning, where the idea is that you can basically come up with some proxy tasks. In the case of single image self-supervised learning, either augmentations or different tasks where you can learn the core of the representation without any supervision. And then you always need, of course, some labels in order to sort of associate the language with the semantic categories. And it turns out that there has been a lot of attention when it comes to self-supervised learning for image classification. And those are the settings where, again, every image just has a single label. We've also looked at settings for object detection. But in all of these cases, the self-supervised learning techniques typically consider a single image, right? And they either work out on some augmentation, use these ideas of contrastive learning, where you need to sort of pick some positive and negative examples in order to formulate either some pair laws or triplet laws in order to sort of drive the gradients of the network in order to learn the representation. And so what we were interested in is if we could somehow use the spatial and temporal consistency, which we are all familiar with when you do mapping and structure promotion and localization, in order to use this as a signal for semantic segmentation. And so we embarked on this idea of trying to do a self-supervised training for semantic segmentation in particular environments, where the idea would be take the multiple views, associate the regions in the individual views, and then sample from the corresponding regions in order to select the positive examples for the contrastive learning in order to learn the right representation for semantic segmentation. So there are sort of a couple issues of, how do you select the regions? So in our setting, we used some sort of bottom-up over-segmentation techniques. These are, you can sort of think of a superpixel or the minimum weight spanning tree techniques just to get some regions. We select views from the sequence, which are fairly well separated because, again, there is this trade-off, the wider away apart from each other the views are, the more challenging the correspondences are, but the stronger the signal for the gradient association is. And so once we have these pairs of views, we basically match the regions, compute the intersection of the union of the region, and then explore different strategies how to sample the points from the regions in order to create the positive examples for this contrastive learning. And interestingly enough, it turns out that picking the exact correspondences is actually quite weak signal for sort of assuring a good semantic segmentation, because you actually want some variation within the regions which are spatially coherent. And so then we have this mechanism where we formulate 3 types of losses. One is the exact correspondence loss, where we take exact correspondences in order to sort of take the features computed at the locations and drive the representation together. Then we have a mechanism where we randomly sample from the whole image where these correspondences come from. And then the second component is that we obtain, we also do the sampling of regions, but do not use the exact correspondences. And another sampling mechanism is to assure that the pixels are collected sort of broadly from the entire image. And we use the Barrow twin loss contrastive learning approach, which the advantage is that you don't actually need a negative examples. So it assures it's a sort of a mechanism how to prevent the mode collapse while using all the positive examples. So this was exciting. We managed to train a model, and then we were able to get sort of comparable performance using only 5% of the labeled data. And then again, this is the 5% in the particular environment where we were sort of performing the semantic segmentation, but it ended up being much more effective than actually fine-tuning a model which was trained on a completely different data set. So this was a sort of a little bit of an exploration of how to instantiate some of these ideas of self-supervised learning to video sequences, segmentation, and this data association. There's some technicalities how to do this fast, because in the training stage, this process of computing intersection over union over regions, it's computationally expensive. But this is the sort of the result of our technique. And I can go to details about comparison with the baselines. And there's sort of additional discussion in the paper, which is again showing the improvement in the performance as you label more data. So, and here are some examples of the results. So again, the punchline here was learn things for particular environment, but try to minimize the number of labeled data. and exploit the temporal consistency and also the over-segmentation. And then, these are some more results, just the visualization. We did the initial experiments in synthetic environments because that's where the ground truth labels were available. But then we also evaluated the approach on our active vision data set and another Matterport data set and obtained the sort of the consistent observations about the effectiveness of this technique. So the weakest link, and these are the details can be found in the paper with Sulav and Iman, who were the students who worked on the project. So the main weakness of the approach, which we sort of concluded the development sometimes last fall, was actually the over-segmentation technique, which we used back then. And so now with the advances in these bottom-up segmentation methods, such as the segment anything technique, it's actually without any effort, one can dramatically or somewhat dramatically improve the quality of the semantic segmentation approaches by using the segments obtained by segment anything, and then letting the traditional semantic segmentation models vote for the segments. And this is just literally a couple-day kind of adjustment in the project without even deploying these techniques within the self-supervised learning. So this is just something we tried because we were excited about the new segmentation model. Okay, so, and again, the challenge of actually going and naming everything is still there, right? Because the segment anything gives you the segments, but doesn't give you the names. So right now, this gap between name everything which you see versus what are the semantic segmentation labels available in the current state of the art data sets, it's sort of quite large. And this is sort of something we are excited about and sort of trying to narrowing this gap. So another small component, I'm not going to go into detail, is that other tasks which are of interest and relevance in indoor scenes, for example, pose estimation for objects. And again, if you take the state-of-the-art pose estimation technique, it is often challenging for make it work. So again, we have this situation, do we need to label more data in our particular environment in order to do this? And instead of again fine-tuning and training the entire model, we were interested if we can build an effective pose estimation techniques on the top of these mid-level representations, which have been found very effective for multiple tasks. And here again, the thought was that likely the systems are going to be engage and will be responsible doing variety of the tasks, and some of these representations should be reusable. So we have again trained a very simple model, which really required only sort of couple of fully connected layer on the top of the pre-trained mid-level representations of surface normals and the reshading, and obtain sort of the pose estimates for the basic set of furniture categories. And instead of just taking the top estimate, we took the top 4 estimates and then further refined the estimation, training another model, which was sort of matching the templates. And again, so this is, again, following the line of thought of building these very lightweight models on the representations, which were pre-trained without any labels. And so I'll skip this. And then again, we showed that we can have sort of competitive performance of models which were trained from using large amounts of data. Okay, so let me kind of switch gear a little bit and discuss now this idea of, okay, so we have these models, but these models were created by sort of people moving around and doing the structure for motion localizations and so forth. And so we would like to know is if suppose that you enter some completely unknown environment, which you have never seen before. So can you use some regularities in classes of indoors environments such that you can actually go and accomplish some tasks in this novel environment without ever building a map? And one such task, which is actually directly related to mapping, would be an exploration task, where you would autonomously move around in the environment such that you will sort of get the coverage. And sort of historically, in this community of embodied vision, people have tackled this problem using deep reinforcement learning. So you have some input representation, the reward is coverage, and you put big model in between. But again, challenge with some of these approaches is that they need incredibly large amounts of data for training. So lots of episodes in order to train these models. So we, instead of taking the deep learning route, we revisited some of these traditional model-based planning techniques and augmented them with sort of a learning-based approach. So let me sort of discuss this a little bit. So here is our problem. There's a mobile agent which is placed in the environment, and it needs to explore the environment. And suppose that there is a time limit on when you have to do this. And if the time limit is large, then of course you can explore it completely. But the point is that there is some criterion which you would like to optimize. So what we would like to, so you need to make some decisions, right, where to go. And these decisions should be informed, because clearly, imagine that you are going down the corridor. If you're going to enter every door where there is a tiny little closet, you're going to spend a lot of time exploring, but you're going to have a very small coverage. While it's probably much more effective to head to the directions where you have likely large open spaces. So these are some of these intuition our technique try to capture. And so the formulation is the following. So these exploration techniques have been historically tackled using these frontier-based approaches, which means that you are locally at a particular location. You look at the frontiers, where frontiers are boundaries between seen and unseen space. And here we have a location of the robot, and we have 3 frontiers, the yellow and 2 green frontiers, and you need to decide which frontier to select, right? And if you were to be greedy, which is what majority of techniques in the literature try, that you would just go to the nearest frontier, right? And greedily keep on doing it. So, however, what we would like to do, we would like to be a little bit more informed how we select this frontier. And so instead of just doing a greedy search, we want to formulate this as a Markov decision problem, where we are going to simply try to choose an action in order to maximize the expected utility. And this is typically formulated using Q-learning problem. And in the traditional setting, the Q function, which is characterizing the value of the action in a particular state, is characterized by a Bellman equation. However, what happens in a basic setting is that you don't know transition probability and you don't know the reward. And this is exactly the starting point where all the reinforcement learning techniques come, and they just sort of run a lot of episodes and using kind of the sampling complexity can sort of properly learn the function. So we instead decided that what if we actually learn the reward? And in this case, we decided to sort of learn the reward structure. And before learning it, we need to sort of somehow quantify it. So in our case, we're going to embark on using the actual model-based planner, where the reward is going to be some function of the current map, the action you are going to take, and the amount of time you have before your exploration limit sort of expires. And so if we learn the reward structure with sort of a little bit of derivation, we can also assume, so the actions here, instead of low-level actions, are going to particular sub-goals and frontiers, right? So the action set is dynamic because every time you see a different set of frontiers. And we can actually go and in the training stage, go through a lot of examples where we have a frontier, and then we can estimate the reward of that particular frontier. And frontier and action can be sort of taken as a synonym, because action is basically going to a frontier. So here is kind of a quick version of Bellman equation for our problem, where the state space is the action space is the space of all the possible sub-goals which we have at each instance of time. The state space or the belief state is comprised of the map, the pose of the agent, and how much time you have left for exploration. And then if you take a particular action, the reward associated with that action is the expected amount of space you are going to explore, which is going to get revealed, and minus the number of steps it takes to get there. And then the remaining one is going to be the number of steps it takes to travel, come in and out of the other sort of possible frontiers. And this is basically, we can then solve this problem using the classical Q-value iteration. So what now is remaining us to do is to actually formulate the learning problem where we are learning the reward function and the time how to get in and out of the space. So for learning the reward function, we use our semantic segmentation, and the depth map, which sort of reveals how likely it is that the area which we are facing, which the frontier faces, is going to yield to the revealing of the large amounts of space. And in a supervised setting, we can supervise it with the actual reward, which is the space which got revealed. And then the DN and D out is the space it takes to actually explore the entire space, which is beyond the frontier, which is in our case approximated by sort of solving the traveling salesman problem on the graph. And I just want to remind you that we train these models on, say, hundreds of environments. But these models sort of exploit this general structure of indoors environments and how we make the decisions. And then if we then deploy them, these are some examples of differences between the greedy approach and this sort of informed learn-based approach. So notice that the greedy approach kind of keeps on going back and forth, exploring the environment, and within the limited number of steps, it covers only 76% of the environment, while the other approach is sort of much more informed, goes to the areas which reveal a larger amount of space, doesn't go peeking into the small little nooks and crannies, and within the limited amount of time, explores almost all of the environment. And again, we can guarantee the full exploration if the threshold on the number of steps is, and this is similar case here. So this is, so these are the examples of these exploration techniques. So here is kind of an example of the problem, which using sort of traditional techniques, which are not so computationally expensive, and reformulating the problem and learning the part which is actually quite feasible to learn, we can get a very competitive performance with some guarantees on a problem which has been studied for a very long time, but now we are making that reward sort of semantically informed, because we are learning this mapping between the semantic content and what we see along a particular frontier, and what is the reward or what is the likely space which will get revealed. And so this is what I have. We have some variations of these problems for also point goal navigation. And another sort of, I think, exciting extensions of these ideas, which we are looking at is, here we actually need the mapping, right? But you can imagine that for many of these problems, metric maps are probably not necessary. And so the question is, how to revisit this while relaxing some of these assumptions. And yeah, so this is all I have. If there are any questions or discussions?
Questions? You think today about choosing robots to explore space, and what would be the best you could say human trying to do how to find guys.
Well, so in principle, you could sort of use the same kind of criteria for the human. I think one thing which, so I'm not sure whether the idea of frontier is so clear here, right? Because right now, because the camera is mounted at a particular height, this boundary between free space and non-free space, it's clear. So it probably will be not directly applicable. But you can imagine taking 360-degree of field of view and kind of partitioning it into possible areas and then quantifying that area, whether it is likely to reveal a lot of space or not. And this is basically what we are learning, because we have a lot of simulated examples of the environment where things are semantically labeled. So, so if I have a limited time, I'm not going to be kind of, going to bathrooms and closets. But this is when the objective is exploration. You can imagine that the objective is search, that you are looking for some object. Or you can also imagine that the objective is reconstruction, that you want to, optimize something else. Because in our case, the reward exactly is trying to capture, you get a high reward where you have a high coverage. But you can design different kind of reward structures depending on the task. Okay. Yes. So the generalization of the reward function in this case is measured by the effectiveness of the strategy on previously unseen environments, right? So we learn the reward structure on a subset of environments where we take a lot of examples where we have the ground truth information. How much area is it behind this frontier? How much area is behind this frontier? Then we learned that mapping between the semantics and how much area gets revealed. And then this mapping or the reward estimate is then used in a novel environment. So we do not per se, well, we can also evaluate. I don't have the numbers, but you can also evaluate it. You can have kind of train and tested how well we are approximating it. Yeah, which we do when we are training, but this is sort of not the main objective. Yeah.
Thank you so much. You mentioned a lot about the semantic segmentation.
Uh-huh.
So there are some data sets or some, like in real world, you may have the wall that is, half wall, or there's like some issue with the wall or with the door, like broken door, broken wall. So did you do any analysis for semantic segmentation, that type of objects that we don't have enough?
No. So I think one thing I would like to again highlight is that so the semantic segmentation is this issue of associating some linguistic terms with the regions in the image, right? And in our case, we are doing it for specific environment, right? So we will likely learn that this segment should be associated across the views, but in order to call it a broken door, somebody still has to label it, right? But the advantages of this technique is that the segment association is environment specific. You are not trying to fit to some 20 categories a model was trained on, because majority of the data sets have this, if that makes sense. But it again depends how you set up your evaluation platform. So here the challenge was more how to sort of get the learning work that's sort of feasible. And yeah. Okay. Thank you.
This time your speaker.
Okay, thanks.
Now we have two paper presentations. Invite you on to start the first paper presentation. It's one question. Yes. They just connected to Zoom, which John is on left. And you can show yourself. All lowercase. I think you need to log in.
I use your laptop.
Can you share your slides? Sure. Are you gonna email them to me? Yes. Yeah.
All right.
Here.
All right. Sorry about the waiting. Good afternoon. My name is Yuguang Li. I'm a principal applied scientist from Zillow Group, and this is our intern work over the last year, which is uncertainty guided two-stage room shape layout estimation. Now, the problem we're trying to solve is given a 360 panoramic image, which is straightened, which means the North Pole is pointing upright. Given this image, we want to get a 3D room shape out of it, which, as you can see, it's a polygon with a height that's lifted up. And from the passive research, horizon-night, layout night, let's start from that. They translate this problem into a 1D regression problem, which looking at this image, every image column, we're predicting 3 channels: floor wall boundary, ceiling wall boundary, and the corners. So they regress the floor wall boundaries, ceiling wall boundary as a regression problem, and the classification problem as the corner prediction. So once you have that, there is a post-processing. You can get the polygon piecewise planar representation of this room, and you lift it up with the ceiling height. So from the previous work, that's what the HorizonNet is doing. HorizonNet is also the work which we're based off. And then the past year, there are state-of-the-art papers, LED2Net, which use differentiable rendering and then produce really great results, and LGT. net, which use shift the window block and the global block vision transformer to get also the state-of-art results. So the motivation of this work is we want to, so we run HorizonNet on our data set, the low indoor data set, and we realize that there is a lot of large space, which means there are some walls that's really far away from the camera. And the further it goes, actually due to the projection of the image, the more air from the top-down view it magnify. When we look at the data distribution, so this is a histogram created using the Zillow indoor data set and Structure 3D data set. Data is imbalanced. Now the x-axis is of all the image columns, the depth distance, and then the vertical axis is histogram. As you can see, 90% of walls from Zillow indoor data set is under 4-meter distance, and there is only 10%. That's far away, but those really hurts the IOU evaluation from the top-down view. In order to address the further, the larger room shape, we propose a 2-stage neural network course to find. As you can see, there is an initial stage, which is the architecture is a modification of HorizonNet, which produce not only the floor wall boundary of the room, but also the uncertainty of each per column prediction. So the red line is the mean and the prediction, and the green line is the upper bound of our error that we can actually predict. And we use that to guide a refined stage. Now, the refined stage is really, it's a similar architecture to the initial stage. It's trained differently, but it can do much better than on the far away area. So we use that uncertainty to guide the refined stage, and using this merging stage, and we'll produce a results that's doing good in close and further walls. So here are some details about the initial stage and refined stage, and you can see initial stage really does well for the distance for the image quality under 4 meters, and the refined stage does better for the far away. So out of these two networks, they're really similar. It's all applied to full panoramas, and they all have a modified height compression module, which we'll expand in the later slides. And the initial stage also produces uncertainty prediction. Refined stage use a different loss, and it's trained differently, which focus on faraway regions. And the merging stage, we explore different ways training end-to-end, but at the end of the day, we run out of time. The heuristic merging works the best, which use uncertainty and the distance. So with that, we produce, like the combined results. Now, as we said, both stages are a modification of HorizonNet. Now, the modification comes from this height compression module. This is something we tried, and it produced better results. That the height compression module, it goes in. There is a flatten. There's a flatten operation 64 times 2. There is this 256 times 2. There is a flatten operation to produces 256 channels, but we realized that flatten is actually not as good as direct convolution multiple layer. So that's one thing we discovered that's doing better modification. The other thing is the uncertainty prediction. So we realized all the regression problem, you can not only just model it as a regression problem, you can modify it to actually produce a Gaussian distribution, which is composed of mean and standard deviation. So instead of produce one value, we actually produce 2, using this novel negative likelihood loss during training. So that gives you an upper bound and the prediction. With that, when we switch to that the NL loss, actually we realized that for the closer walls, the initial stage actually does better than without this new loss. Another thing is for the refined stage, we tune the loss in differently that we wanted to focus on faraway area, and which really from the top-down view, by only looking at the pixel loss, that's not sufficient. So we actually go to the top-down view and do the projection and measure the distance in the top-down view and use that as a loss. And we realize, and we discovered that for the refined stage, far away area really have a gain when we use this top-down loss. So refined stage does better in the further area, and we combine them. That's that we produce better results in LED net and LGT net. So to recap the contribution we have, we produce a two-stage neural network which produce certain results, and there is novel loss on predicting the floor wall boundary uncertainty. And we slightly modify the height compression module, and this is and the merging stage is really efficient. So there's more results, qualitative results, examples. As you can see, our results at the last row, it really does better in the room shape that's quite large. Another row of results, as you can see, it does better for the closer wall and the further wall. And as you can see, the original LGT net and horizon net, they all have these issues. Some failure case, these are examples of it, but mostly due to the object that blocking the view produce this these errors. And that's all for this work. I'll take any question.
Great. So we invite our next speaker. I see that you're joined. You can go ahead and share your screen.
From intelligence from corporation, we would like to talk about our model for room layout estimation of vast calculation. The task of estimating room layout from a single shot panoramic image has an application such as augmented reality, virtual reality, and furniture arrangement simulation. Since the room layout varies slightly, deep learning has been successful in solving the task. Most studies have estimated room layouts by detecting room geometry components, for example, wall boundaries and corners. Several image has an occlusion like this in the red box. The occlusion reduces the estimation quality because it has room components, but it has not been addressed explicitly. This problem occurs because single-shot images are used as input and there's no other data available to compensate occlusion. Therefore, we use 3D data obtained from drawing as additional input to compensate the information behind occlusion. However, using 3D data raises two issues. The first one is just feeding 3D data to a model does not guarantee it will use effectively. So we introduced an IE loss so that the model can use 3D data. I will explain the details later. The second issue is that in Python, there are cases where the drawings are not available or the layout is different from the real one. To deal with those cases, we propose a model using knowledge situation that is trained with an image and 3D data, but does not require 3D data for inference. I will explain purpose IO loss here. 3D IO loss evaluates how much two spaces overlap, so IO loss can account for the error in 3D space. To acknowledge the IO loss for room layout estimation has not been proposed because the proposed one, the already proposed one, is for keyboard objects. Thus, we propose an IO loss that can be applicable for non-keyboard rooms. This is a simple calculation. First, cut out a room into rectangles and calculate IO on each rectangle, and finally integrate them. Our proposed model using knowledge distillation is shown here. Knowledge distillation, the larger model is called a feature model and the smaller one is a student model. First, we train a feature model which takes images and 3D data as input. For 3D data, we feed point clouds representing all boundaries like this. And then we trained a student model that takes only images as input and perform inference. We use cutout augmentation, which masks arbitrary area by black square to generate pseudo occlusion. For loss functions, besides IO loss, we use boundary loss, boundary and corner positional loss, and feature distribution loss for the training of the student model to transfer the training results of the feature model. Show quality results using one of the benchmark datasets for 3D. Green lines indicates the estimated boundary. Blue is the ground truth, and white lines is the color bar at the bottom of the image, show the corner positions. The red boxes around the occlusion areas show our model improves estimating, particularly at these occluded areas. Quantitative results are summarized here. We evaluated the data on panels 3D, a data set containing only keyboard rooms, and on motherboard 3D, a data set containing non-keyboard rooms. We use the metrics often used in each data set by other models, like for panels 3D, we use pixel error, corner error, and 3D IO loss. And for motherboard 3D, we use 3D IOU and 3D IOU for evaluation. A model outperforms other models on each data set besides pixel error on TV or on panels 3D. So corner errors are for the errors that evaluate in all boundaries and position corner errors onto the image. So, and these errors do not always improve simultaneously with 3D IOU. Thus, we concluded that our model was effective since the metric for 3D improved. Since our model tackles the occlusion problem, we tested models on a data containing only occlusion. Since the panels 3D contains only keyboard rooms, which has no occlusion like this, we only extracted occlusion data from the manifold 3D. The results show our model performs others with these improvements. The improvements are greater than those on all data in manifold 3D shown in the previous slide. This indicates that our model is particularly robust to occlusion. Here, we visualize the model's attention to see the model's effect on occlusion. To visualize the attention, we calculated integrated gradients, which explains the relationship between input and model's prediction. For the visibility, we calculated the area integrated gradients of the model, estimating corners. The darker areas remarks high value of integrated gradients indicates that the model has higher attention. A black area enclosed by red box indicates that the model has more attention to the area of occlusion, which might contribute to the model's performance on occlusion. In addition, the diffusion of black area of a model suggests our model might capture the geometric relationship of root components better than other models. Finally, population studies confirm the effectiveness of each method. CUT, KD, IOU stand for cut out, noise distillation, and iron loss, respectively. The introduction of individual functions alone has improved accuracy, especially KD plus IAU. It indicates the additional input of 3D data is used effectively with the IOU loss. Here's the conclusion. Occlusion degrades the room estimation quality. To handle occlusion, our model takes 3D data as additional input. IOU loss is proposed to guarantee the use of 3D data by the model. Furthermore, assuming the cases where 3D data is not available or different from the real layout, we use knowledge distillation to transport the results training with 3D data to a model with using only image. As a result, we were able to construct a model that is robust to occlusion. That's all. Thank you. Do you have any questions?
Great, thank you so much. We are gonna take a short break now. We have two more talks. This one starts at 4. That's gonna be a visual, then followed by another intense talk. We're gonna restart at 4 p.m. Yeah.
Really cool. You can see that. Yeah. So, yeah. Thank you for the okay. You can actually mean this. Okay, so they leave this. Yeah, we just stand up.
Yeah, this. Did it for the speaker part, yes. You just stop there. I'm gonna start with the whole thing in the file. Oh, I see. Yeah. But I don't know. Yeah, as well. Story is here. Well, I'm sure, but for a lot of people, I am. I think I'm gonna.
All right.
Hey, Zihan, can you hear me?
Hi, yes, I can hear you. Who was
Okay,
speaking there? I can only see the name CVPR.
this is Naji. I just turned my camera off so that we can see you. Thanks for joining.
Hi, thanks for inviting.
Of
It's nice to
course.
see you.
All right. Okay. So we have people here in the room and also virtually. Welcome back. Our next talk is a virtual talk by Zihan. He's a chief scientist at the Manicore Tech Company. You probably know him by his great work on structured 3D and a lot of great following work after that. Like almost all of our speakers, he doesn't need an introduction as well. So it's all yours, Zihan.
Okay, so I'm sharing my screen. Can you see that?
Yep, we can see your screen.
Okay. All right. So thanks again for inviting me to this workshop, and thanks for the great introduction. Okay, so my name is Zihan Zhou, and I'm from Manicore Tech Incorporated, also known as Kujala.com. It's my great pleasure to be able to present at this workshop because it's closely related to what I'm doing and what our company is doing. But unfortunately, I'm not able to attend the workshop in person due to some conflict in my schedule. I really hope to see everyone's face, but it seems like the Zoom does not allow me to do that. But hopefully you have enjoyed the workshop. All right. So let me start. Okay, so the title of my talk is Towards AI-driven Compute-Aided Interior Design. So before going to the topic, let me briefly introduce my company. The Manicore Tech Incorporated is a world's leading cloud-based SaaS design platform. So it's mostly focused on cutting-edge research and development on the application of design platforms and the 3D content creation. So as you can see in this picture, at present, we have several business brands such as Kujala.com, Kuhome, and Modelo, and Meijian. And we are serving like more than 200 different countries. And probably the most well-known brand of our company is Kujala and Kuhome. So they are mostly focused on the interior design, especially home furniture solutions. So so designers like our users can use our platform to conveniently create like 3D home furnishing solutions, and then using our high performance computing rendering devices to engines to create the design result like visualizations. And currently we have empowered more than 8 million users and cooperate with more than 30K different business brands. So in terms of the average monthly active users, we are actually the largest platform in the in the worldwide 3D interior design, decoration, and construction industry. Okay, so let me first show you a quick video to show to illustrate how the people like the designers using our platform to create like home interior design results. Okay, so you may notice like there are some Chinese interfaces in these videos, and then in the future videos I'm going to show, because some of the functions are still in early development stage and only available in the Chinese version of our platform. But don't worry, I'm going to explain those contents in the videos. Okay, so let me show this quick video to you quickly. Okay, so as you can see the video, like designing a home furnishing solutions in our platform is actually quite simple. So it consists of three major steps. So the first step is to create a floor plan for the home. And usually people can do that by manually create like walls, windows, and doors on our platform. Or they can also upload like CAD drawings, and they will be automatically converted into a floor plan in our platform. And after that, people can use our platform to place furnitures and do the decorations, like manually by selecting like furniture, like products, and then put into the 3D space. And finally, they can choose the correct lighting design. So they will put some lights into the 3D space so that the room is properly illuminated. And then they can hit the rendering button and it will give you the final result. So that's what the three steps. So in the next, I'm going to so my talk will be divided in roughly two parts. In the first part, I'm going to describe what we have done to use artificial intelligence and machine learning to help people to speed up this process and reduce their workload. And then after that, I'm going to share some of my thoughts on how the machine learning may change our the platform and the computer aid in the design in general in the future. Okay, so let's go with the first part. And we have done work in all the three steps. So let's start with the first step, which is floor plan creation. So let me first briefly introduce this problem. This is actually a very quite actively researched problem in the past few years. So the goal is to create a reasonable floor plan design, like where the rooms are, given some input constraints. So some of the most common constraints, including, for example, the room boundaries. So in 2019, colleagues in our company and some other people have, started this direction, and we have probably created one of the earlier data set for this problem for data-driven method that's called R-plan data set. And on the right, we can see there are methods which takes the bubble diagram as input. So here, the bubble diagram is like a graph where each node indicates a room type. The color indicates the room type, and the edges indicating how those rooms are connected. So given the bubble diagram, there are methods which can convert the spiral diagram into actual floor plan designs. You can see that this is mostly considered as like a graph constraint generation problem. And yeah, you can see probably some of the works that also close related to the speakers in this workshop. Okay. And also there are methods which can do free generation, like they can take no inputs, then start from generating from like just first the rooms, which are represented as rectangles, and then the relationship between rooms. And finally, they use the optimization method to optimize the locations of the room according to the constraints and relations. So anyway, so the goal is always to create the floor plan. So the floor plan, and depends on what the controls would looks like, there are different methods. Okay, so we have also create a system which can create such a floor plans. So let me show you a quick video on this one. Okay. Okay, so here I can see like the people are actually selecting the overall size of the floor plan and also indicating how many rooms they want. And actually this is an interface for the Modelo software, which is also a brand in our company. And what this Modelo is doing is actually creating a 3D creating a 3D design for small to medium sized houses and buildings. So you can see that once we given those constraints, they can generate floor plans automatically using our AI algorithms. And the people can choose from different floor plans and see which one they like the most. And once they decided, they can simply create the select button, and it will automatically convert that into a house. Okay. So this is what we have done in our company to actually incorporate those floor plan generation algorithms into our platform. So once you have the floor plan, the next step is probably to put the furniture into it, right? So now the input would be a floor plan, and the output will be a completed furnishing design. So we divided this into 2 steps. The first step is to generate a furniture layout from the floor plan. Okay, so let me show you a quick video on the left. So it's actually very fast on our platform. You just simply, since we already have the floor plan, you just simply click the click the button in our interface, and it will automatically create the furniture layout. It takes less than 3 seconds, I guess. And you can also select from multiple solutions. And then once you have the layout, the next step is to really choosing the correct the furnitures you like. And in this step, we allow the users to browse through the existing designs in our platform. So remember, one of the benefits of using a cloud-based design platform is that you can browse through all those designs from previous designers, and you can choose which style you like the most. And once you decide, you can easily click the select button, and it will map those styles to the design of your house. Okay, so let me show you a quick example here. Again, it's very fast. It takes less than 5 or 10 seconds. Okay, so now you have the complete furniture design. So in all, so so people can design us. If you use this our AI algorithms, they can probably complete the furnishing design in 10 seconds. And this has been already been using by many designers on our platforms. Okay, so that's the second step. That's to complete the furnishing design. The last step is to do the lighting design. So this is actually a area where less people are, has less been, explored. And this year, colleagues in our company and is collaborating with people from Zhejiang University and the Ray Engine Tech Inc. And they have published a paper in Transactions of Graphics on this topic. So I think this is very interesting one. So I want to explain a little bit to all of you. So the problem here is now you have the furnitures in your rooms, but in order to get a visually pleasing rendering result, we need to have the correct lighting effects. So this is actually a very challenging problem because we have to first decide how to place those lights around those rooms. So there are all different kinds of lights, from exterior lights to interior lights, and they all have different effects. And the second, we need to optimize the light emissions, like the intensity and the color of the light, so that it will create a visually pleasing result. But those design principles are very sometimes are very hard to describe. So previously, people have been basically using heuristics and the rules to generate those lighting designs. And in this paper, the authors have presented a data-driven method to automatically generate the lighting designs. So first of all, the first contribution of this work is large data sets, which consists of more than 6,000 interior scenes waiting list layout designed by professional designers. So here we can see it consists of the interior scenes with professionally designed lightings. And we use our high performance render engines to render high quality images, as well as the illumination images for each of the lights when they turn on and off. So those are training images and the ground truths that we can use to train the neural network to predict the lights. And the second contribution of obviously approach to do that. And here it takes a two-stage approach. So the first stage, it focuses on light layout arrangement. So giving the input furniture, input room with furnitures, it predicts where we should put those different type of lights. And here, the challenge here is like the lights should be, light arrangement should align well with the room structure, as well as the furniture already exists in the room. And so in order to do that, they choose to use a iterative method to recursively place more and more lights into the rooms. And in the second stage, it's generating generating the light emission parameters, which include intensity and the colors. The idea is to basically given this light arrangement, first trying to generate a guidance image to which is basically image like indicating what the ideal light will be if the parameters are optimized. And once with this guidance, they use an optimizer to find those parameters. And that's and once they have the parameters, they can use that to illuminate the room and get the final results. All right, so I'm not going to go into too much details, but this is actually works very well. So here I'm going to show you some quick examples where it compares the lighting design from the algorithm versus the lighting design from humans. So you can see like first of all, they have share a lot of similarities, indicating like the algorithm actually learning something. And also sometimes you can also see the result is actually sometimes could be even better. So obviously that's subject to different criteria, but you can see that they look pretty good. Okay. So just to summarize a little bit, so what I have described is several different algorithms that can generate 3D interior design in several steps. But actually, what we have learned through this process is that they actually share a lot of similarities, although they tackle with different problems. So what they all share is, if you look at those 3D design, they're really just a bunch of CAD operations like people have to do, on our platform in order to create those designs. So what we have done is to using a deep learning models like transformers to learn from those operations. For all those different problems, we are all doing this. And once we have learned that, we can leverage those learned models to generate 3D design. So that's really what we have done. Okay, and and the core of all those algorithms is so-called domain-specific language, like the language we have to use to create to tackle those different problems. So here I'm probably going to skip those slides, but here I just want to say like, for all those different problems, once we choose the proper DSL, the domain-specific language, the models can be relatively straightforward, like relatively consistent across all the different problems. And we found actually when we have all those different data that are learned for the same model, it's actually getting better results than you try to learn from for the different problems. Okay, So just to quickly brief summarize. So we have tried to generate 3D content with those different domain speaker language for different domains, like for lighting, for furnitures, and for floor plans. They all there are some strengths for those methods. The most important one is probably the controllability that because it's straightforwardly you can align that with CAD tools and commands. And also we find that it also has possibility to explain its own behaviors. So this is quite similar to what people have discovered in those large language models like GPT. So where sometimes it can generate output that are consistent with the previous ones. Just give you an example. So when we generated the furniture, sometimes, for example, like a bed in the bedroom, we found sometimes they generate a bedside table and sometimes they don't. So if we just look at the layout, we don't know why. But if you look at the actual furniture, so it generates together, can see sometimes the furniture actually has a bed and bedside table bundled together. So in that case, they will not generate another bedside table for that. So that's kind of like a consistency across different models, like the layout and the furnitures. But also it has some weakness. Probably the most important one is it's still limited to the data we have. So which are those designs created by professional users. So that's still, although the very large scale, we already have large scale data, but still a little bit limited in terms of the variations we can generate. Okay. So in the next maybe a few minutes, I'm trying to share some of my thoughts on how to fix some of those problems. And this is obviously something that people has been very excited about and been using a lot. That is the text to image generation with diffusion models. So probably most people are known about this. So I'm not going to explain that. And with that, people has also been able to use text as controls. So the idea here is to use like multimodal network like CLIP to match the line those text input with images and the idea is to generate embedding that which can be used as input to the diffusion models or generative models for the images. Okay, and if we look at like a real platform that has been really widely used, that will be Midjourney. And we see that it actually takes one more steps. Here, what they do is they actually can naturally navigate between all different two different modalities. That will be text and image. So for example, from a text, we can use Midjourney to generate the image. And if we want to make variations of this image, we can add more text. So with this same image and a new text, it will generate a new image. So that shows how they can navigate from convert one modality from text to images. But also you can also change you can convert images into text by showing like, okay, giving this image what is using this described command in Midjourney to generate text. And you can do it so on, and forever, actually, you can do that. And this is actually very appealing to designers because that's justified by a lot of people using that platform to really actually do their creative work. So what we have learned from this experience is like the image synthesis with diffusion models are actually very good at generating diverse results, but still have some limitations in terms of the controllability. And actually, we found that they actually complement with the 3D generation algorithm we have. So that actually inspired me to explore possibilities to to integrate the 3D generation as another modality into this full pipeline. So instead of using the 3D generation to generate all those designs, we probably want to use all those, combine those different modalities. So we have done some work on this in this direction. For example, we have trained models to align large language models with the 3D generation models we have described before. So now we have a new version of the software which can still generate floor plans, but this time from natural language descriptions. So here the description is unfortunately in Chinese, but as you can see, so here basically what this user is saying is how many zooms they want and what types of and then several requirements, like how many people are there in the family, and the algorithm will automatically decide how many rooms they need, and again, so they will generate several different floor plans. Okay. And we have, once we have those 3D designs, those floor plans, again, we can generate a room layout. And from here, we try to think about how to incorporate that into image synthesis algorithms. So you can see here, the idea is we can use that as a control to generate synthesized images. So let me show you an example. So here we have a room layout, but without actual furniture placed, just like models. And now we can use like a method like stable diffusion to automatically convert those line arts or wireframes. Yeah, into images. Okay. Okay. So now we have seen how to navigate from text to 3D designs and from 3D designs to images. Actually, we can also navigate from images to 3D design. So this is actually just a 3D reconstruction problem. So given the image, even as a synthesized image, we can, using our 3D generation models to map that into an actual 3D design. So this way people can use this, can use that in downstream CAD applications. So as we have seen, the 3D design basically consists of layouts and furnitures. And we can also do this for panoramas. So if we have panoramas, we can generate 3D designs automatically from that. That's all like just basically driven by models that which you can learn to map from one modality to another modality. And all those functions can be done using a single 3D generation model. Okay, so let me summarize. So in this talk, I trying to share some of the work we have done in terms of generating 3D content from user input. And we also have been inspired by recent development of image-based conditioned image synthesized networks like diffusion models. And with that, we actually have been able to think about there might be a way we can put all those things together. That will be a future, maybe a future AI-driven computer-aided design interior design platform, which instead of asking users to interact with the 3D platform, it actually allows the users to interact with text and images, which is much more easier. And in order to be able to do that, we have made several important changes. So the first one is a very important one is this 3D design copilot, which is actually built upon the 3D generation models we have been I've been describing. And here the key is to be able to mapping from one modality to another modality without any extra efforts. And also we have seen that means a lot of things. First of all, the CAD software will no longer need to interact with the users. Instead, the CAD software will be interacting with algorithms in the future. And the next, and also we can see like the rendering and image synthesis are actually the boundary between them will be less and less visible. So sometimes we generate images through image synthesis. Sometimes we generate images from rendering, but you know, that's very flexible to choose in the future. Okay, so with this framework, I want to conclude my talk. So thank you very much, and I'm happy to answer any questions you may have.
Thank you. Do we have any questions for our speaker? Yeah, 2 questions. Do you mind using the mic?
Hello. Could you please explain a bit more about this, like for render from diffusion, how it goes back to CAD? So do you actually generate simultaneously like CAD representation with the diffusion, or is like kind of segmentation model, or?
Sorry, I cannot hear your question very clearly. Can you say it again?
Yes. So my question is from the render, from the like stable or whatever diffusion render journey, you go for the back to the CAD model to have
Yeah.
this 3D segmentation everything. So how you do this? Is it like a segmentation model or something more fancy?
Are you talking about this?
Yes, exactly.
Okay. Yeah, so that's actually you know, that's kind of straightforward to remember. We have a 3D generation model which can generate CAD models from floor plans to furnitures and to lightings, right? So that will be you know, you can consider that as a decoder for this problem. And we just need to append encoder like image backbone, which will be able to recognize those image, and then it will convert this image into a letter code, and then we use that letter code and using the 3D generation model we described before as a decoder to create this design. So we just basically reuse our 3D generation models, but with a backbone from the images. Does that make sense?
Thank you. Yeah, thank you for the wonderful talk. So my question is mostly on how you deal with like broken generated shapes, because when you compare those kind of CAD generation to image generation, the room for error is usually much smaller, especially in the domain-specific language representation. So in that case, do you think there are like systems that you can enforce so that you know, you don't go into those kind of bad regions easily, because then like maybe 50% of your generated data will not be valid anymore?
Sorry again. Can you please repeat your question?
Sure. Yeah. Sorry. So my question is like for those kind of generated data, like some of them will be invalid because say you're doing a floor plan and the 2 vertex doesn't connect. So
Okay.
then you have a broken roof or something like that.
Okay.
In those cases, usually you just don't show those generated results because it's invalid. I wonder, do you think if there are like ways to inject those kind of prior like knowledge into your generated model so that it just avoids those bad you know, domain regions, manifold, whatever?
Yes. Yes. That's actually a very good question. The way we able to achieve some of this, like avoiding like invalid floor plans, let me show you, is to design a proper domain-specific language. So As you can see, so the domestic language is actually closely related to those CAD operations we are available, we are providing from in our platform. And with those languages, you choose what can be generated and what cannot. So for example, if we choose to model a floor plan as a like connection of rectangles, and try to train the model to generate the rectangles, then it will not generate broken broken line edges, right? But of course, it comes with a cost. Because if we decide on a language to use, they may not be able to generate everything we want. So sometimes, in some extreme case, I would say there might be rooms that are not closed, and in that case, the domestic language that's built on the rectangles will not be able to cover it. So there is a trade-off. So we can have a very flexible language to use and to generate, but sometimes we generate invalid result. And sometimes we will choose a more strict language. In that case, we will be able to avoid many of those problems, but also restrict what we can generate. Another way we can do to avoid some of the problems through like post-processing. We obviously will be able to do some check-ins, rule checks, like to make sure those rooms are valid. If not, we will throw it away because it's just a generation model. So we can generate many candidates and choose from that. So that's provide us with the possibility to generate to delete or to throw away some of them. We just basically throw them away. Yes.
Thank you.
Thank you, Zihan. We have 2 questions in the chat. We're a bit late. Do you mind, trying to answer those really quickly so we can move on to the next talk as well? Can you see the chat?
Yes. I see a question from Yasu and from Mayu.
Yeah.
Okay. So the first question is, how do you solve the problem of how to see images to make it compatible with 3D? And I think this similar questions. Can you explain again how you obtain 3D models to train? There are different problems. Sorry. So let me explain answer the first one. So that's what we just trying to explain. So the key is to append to it's just treated as a problem that convert one modality to another one, right? So we have seen a lot of work in now. For example, we can generate images from text. The way we do that is to using a text encoder to encode the text, and then using a image decoder, like a generating model for image to generate images. We want to do that. So same thing we can apply to image to 3D model generation, right? So we use a image encoder. That could be just a backbone from some pre-trained models, like large backbones for image processing. We just use that as a encoder, and then we train the model to map that encoder to the CAD model sequence. So CAD model output, which is essentially the same output we used for the floor plan generation, for the furniture placement, and for the lighting designs. Yeah. Okay.
Thank you so much. Let's thank our speaker. Thank you,
Okay.
Zihan.
Hi. Yes. Yes, I can hear you.
All right. Thank you so much. We're gonna move forward to Yasu.
Okay.
If you don't mind, stop sharing your screen. Zihan, thank you so much.
Mute my mic.
Mic and speaker, please. Yes.
Oh, you mean my laptop is
Yeah,
muted?
yeah.
Okay.
Everything should be muted there. All right, our last talk of the day is Yasu. He's an associate professor at Simon Fraser
Yeah.
University. Thank you. It's been a long day. And he is one of the pioneers of working in analysis and generation of floor plans. And I don't think he needs an introduction. So all yours.
Thank you, Najid.
Thanks all for sticking around. It's getting late and getting tired. So I'm Yasu Furukawa from Simon Fraser, which is right there. So welcome to Vancouver, first of all. So I don't usually give technical talks. This is going to be highly technical. The details are in the papers, but I'm trying my best to explain what we discovered for the past year. We all know that generative AI is exploding. These are one of the few favorite examples on the web. These are fake, as you know. Very impressive, really mind-blowing. And something non-photorealistic, also pretty cool. And something highly controversial, all fake. And pretty, again, mind-blowing. So underlying these results, amazing breakthrough, are the diffusion models. And this website keeps track of papers that are to do with the diffusion models. And most of them are actually the past 2 years, from 2021. Pretty amazing. But these papers are mostly about generation tasks, using diffusion models for, say, existing generation tasks, a best number paper, those kinds. And shamelessly, my group also contributed to the list here, say 2 papers. What I want to convey today is diffusion model is not really just for generation, potentially or likely for any other task which you might solve. Reconstruction, pose estimation could be actually the state of the art by using in a special way. In particular, our group worked on using diffusion models for generation, of course, reconstruction and also pose estimation, which is a bit misleading, but arrangement estimation, as you see in the 3 videos here. Unfortunately, I don't have time to explain all 3, so mostly focus on the reconstruction task and briefly touches generation and the pose estimation or alignment estimation. And our group cares about focuses on structural geometry. So we are talking about reconstruction, generation, or alignment of the structural geometry, or CAD or BIM, which are like these models. Well, you have seen many of the models today. So unlike Earth, these are not structured, a bunch of polygons or the scalar field in a volumetric field. These are kind of CAD model, which you kind of know what we are talking about. So let me first explain generation briefly, then reconstruction, which is the main dish for today, then a bit of time for the last arrangement estimation. Which is the work done by my students, Sapir and Amin, this CVPR. So you can see the details for from this conference presentation. So briefly, this is a full slide, if we really go deep. There's something interesting, but I have to skip again for today. And the research is not like the following. So you have seen many of these papers. You're going to see many of these papers from today. So we have a new tool X and apply to existing task Y. Best numbers, paper accepted, the whole bunch of these kinds. Kind of boring. X can be this, Y can be that. In particular, I'm talking about where X is this, Y is this, but actually not real. Well, it's kind of this, but additional thing, very interesting. That's our paper is about. But again, I have to skip for what's interesting here. But in short, we are generating floor plan in vector format. It's basically a bunch of coordinates of the corners of a room. So initializing all the coordinate by Gaussian, 0 mean unit variance Gaussian, then learn to denoise it. Eventually you get like a floor plan model like this. So without, just don't worry about left and right, just looking at the left, for example, starting from all the coordinate Gaussian, they learn to denoise it and then produce kind of very good floor plan. And that's much better than the GAN-based approach, which we had at the state of the art. And just more examples. So for example, starting from, again, pure 0 mean unit variance Gaussian per coordinate, denoise to get something, and much better than the other techniques. I guess another slide of more results. Oh, 3% done, yes. So that's very quickly generation, and highly expected. You see stuff like that in this conference, say for document arrangement generation, say web design, where the text box, we have images, pretty much the same thing happened. Diffusion model better than GAN, kind of same stuff, essentially. So I want to spend time to talk about reconstruction. What does it mean to use diffusion model for reconstruction tasks? And this is the work done by my student, Jia Chen, and by Greg Mori's student, Luisi. And it's an archive. So in the previous, the work I skipped skim through very quickly. In short, generation was like that. You have certain noisy coordinates, star, time, t. We have some machinery to estimate the amount of noise, kind of correction term, say delta t. Then remove the noise and make t minus 1, repeat. Basically, it's mathematically a bit different, but that's basically the diffusion model. Give xt, infer the amount of noise, remove it, repeat. That's basically the generation. And we have some DNN, whatever, can be convenet, GNN, something, but right now transformer is the best kind, so that's transformer in our case. So if you want to think about what's reconstruction, not generation, one typical way to think about reconstruction is a conditional generation. So in addition to the noise vector, there's the condition, sensor data. Say sensor data from the LGBD camera or Matterport devices, some sensor data as a condition. And given this conditional guidance, you're going to generate a floor plan, but this has to be a unique solution because given the sensor data, there's only one solution. So when you learn to denoise, you are going to get a single unique answer, as opposed to any realistic floor plan can be an answer for generation. So just sensor data as a condition, we can think of reconstruction as a conditional generation. Just condition turns out to be so strong every time, so only one solution is possible. That's one way to think about it. But if you think about this way, actually diffusion model doesn't work to solve the reconstructions, the inverse gap or scan to bin. And there are two reasons which I'll explain carefully today. So first, let me step back and can explain what the generative model is doing. You may see this in your machine learning class, the vision class. So say you are generating 0.1 megapixel image. Your basic generative model basically takes the 256 dimensional space, Gaussian distributions, mapping that into our very thin manifold in 100,000 dimension, because 0.1 megapixel, 100,000 pixels. So generative model takes this distribution Gaussian, mapping into super thin manifold in very high dimension, 100,000. In our case, we actually work on not image data, vector floor data. So dimensions are not like 100,000, say 200, or the room corner coordinates, room type, doors, windows, that type of information. So that's lower. But you basically, if you pick this noise vector, generative model maps to this floor plan. Pick another noise vector that maps to another. So generative model is a mapping from Gaussian distributions to thin manifold in some higher dimensional space. That's what you can learn in ML class. So if you think about what's reconstruction, we now have a guidance or constraint, which is the sensor data. So now given the sensor data, the answer has to be unique. So given this noise vector, under the guidance, when you generate, you have to get this as an answer. You change your noise vector here, then the answer has to be the same thing, actually. So whatever noise vector you pick it has to always go to the same answer, guided by or constrained by the sensor data. That's the nature of the reconstruction task. So very different from the generation task. And of course, if so this data, this maps to this, when the guidance sensor data changes, the same noise vector must map to something different. So this is the nature of what the generative model must learn, given two distributions, Gaussian, the source, target manifold, how the distribution should be mapped to. What you have to learn is different from generation to reconstruction, very different. And interestingly, so this way of thinking, generation is this, and then reconstruction is just adding a condition here. And train exactly the same way, because these days transformer is very powerful. This condition is just cross attention layer. We got the architecture to solve this by transformer, adding condition as a cross attention done. You train exactly the same way. Then as of last year, in terms of CAD model, both generation and reconstruction, I guess state of the art, all kind of our research group's results, but state of the art are from the same method, exactly same training procedure, same architecture, achieve the state of the art for both generations and reconstruction for structured CAD model. So last year I was giving talks, so I make a prediction for the next year, the CVPR. Generation, yes, diffusion model must be the best, so no question. Whatever we do DM, yes, this is going to be the state of the art for generation. Reconstruction, I predicted the same thing. exactly the same DM procedure, just cross attention the condition, tensor data. You get the state of the art for the reconstruction. It didn't happen. You have to do some changes, not exactly equivalent. But autoregressive transformer is SOTA last year, exactly the same, which was very surprising to me. The first time, two different methods, reconstruction generation, become the same, exactly the same last year. And I predicted it's going to be the same exactly this year. The DM, it was wrong, slightly different. So we branch out. So that's what I'm going to try to talk to you today. So first of all, why? That's a question. And exactly the same thing works for autoregressive transformer, but didn't for diffusion model. Honestly, I don't know. So I'm not a mathematician, so I really don't understand how things work. We just discover and report what we discovered. So I'm not trying to really say I understand, but I try my best to explain what's really happening. So now coming back to the example, so reconstruction was like that. You have a noise vector, you have a condition, and generate, or conditionally generate the flow plan like that. And let me use a bit more friendly example to explain what's happening, which is hopefully more easier for you to understand. So I'm thinking of this, the mapping from the Gaussian to the target manifold is our life. And left are the babies, baby Gaussians, and right is a professional manifold, meaning, let's say this is a baby Michael Jordan. Under the guidance of Phil Jackson, the baby becomes the Michael Jordan, the professional basketball player. And I draw like that. This is the procedure. He is the greatest, one of the greatest basketball player. Let's take the computer vision great researcher, the GC of this conference, Fei Fei. So Fei Fei Li or young Fei Fei Li became Professor Fei Fei Li under the guidance of Professor Pietro Peroni, for example. Or maybe the younger Luke Skywalker became the Master Luke in the latest movie under the guidance of Yoda. So these are the kind of the life. So if you think about reconstruction, what we are saying is these noises very different, but when your guidance becomes Phil Jackson, everybody has to be Michael Jordan, which is hard. It's hard for Fei Fei Li to be MJ. If your teacher is Michael Jordan, it's very hard. Even harder when Yoda is the teacher, but he doesn't say things really open. Very difficult. So this is kind of change reconstruction generation difference. So based on the guidance, the mapping has to change. That's reconstruction. Turns out to be very difficult to learn. Looks like diffusion model prefer to learn the distribution mapped to distributions, as opposed to distribution mapped to a point, in which changes given the condition. That one that doesn't work well. So you want the structure to be distribution to distribution. That's what you want to somehow keep it for the diffusion model. That's one issue. Reconstruction generation is very different. However, the distribution, the maps are very different. And somehow DM doesn't like the reconstruction kind. So the second challenge is about the set nature of the CAD model. Structural geometry is a set often. So given a floor plan which has 3 rooms. So this is one representation. And any actual permutation of the 3 rooms is going to be the valid or the same, identical representation. So given a set, say, floor plan of n rooms, there are n factorial permutations of those, which are different representation, but exactly the same in terms of the floor plan. So our task, say, young Luke Skywalker became Master Luke. This target is actually a set, consisting of a set of elements. So this manifold figure was actually incorrect when I drew this. So what's really true is if there are like 3 elements in a set, there are 3 factorial, 6 possible solutions. So there actually is 1 manifold, sub-manifold, and another permutation variant is going to have another copy of this, which is just different by 1 permutation. Another sub-manifold different by permutation. So there are n factorial small sub-manifold in the space, which is identical copy. And again, everything is a set. So you may think that, oh, this is the answer. All the others are not, but no, everything is a valid answer, exactly the same in terms of the floor plan. So very confusing. So yesterday, when you train it, your target was actually this. Yoda says, this is your supervision target. But this morning, this became your target supervision. Maybe a minute later, this may become the target. So any of the n factor can be the answer in training. It's very difficult to learn. Lots of ambiguity. Here's another challenge of the task. So in short, I predicted last year, DM can solve reconstruction CAD model turned out to be really difficult because it's basically essentially asking faithfully to become master loop under the guidance of Yoda, where the supervision by Yoda may change every second. Then factorial answers, very difficult. So given this, how do you actually maybe make it work? The answer is learn the noise and explain what I mean by learn the noise to make things work. So intuitively, if your sensor data or guidance is Yoda, or say you have some initial solution, which is the Jedi, you kind of know you want to sample noise around here. You may have a young Luke Skywalker or young Obi-Wan Kenobi. You want to sample from there likely. And if your guidance is Phil Jackson, you may want to sample around here noise because baby Michael Jordan or baby Shaq may be nearby. So depending on the guidance of target, you kind of know where you should sample because this noise, similar stuff should be similar. Maybe you can do that way. And the issues of permutation, the invariance or the confusion. So suppose you do diffusion. So these are the n factorial variants, the same thing, exact the same thing, but different representation by permutation. The issue is when you do diffusion, if these things become the same location, it's a problem because denoising about inverse procedure. Imagine these that became the same location. Depending on the superimposition you pick it, your target can be different, become ambiguous. So you do not want these samples to be close. So when you do diffusion, you keep track of n factorial variants. If they get close, that's bad. So we learn to change diffusion so that the permutation variants don't get close. You can handle the issues of the ambiguity. So in short, to learn the noise, what he meant was to learn to initialize noise. Basically, if you know the target is going to be a basketball player, you want to sample noise which can correspond to the basketball player, maybe. And also keeping n factorial permutation variants separated. That's the intuition. Let me explain with more math what we are doing. At the left is the default diffusion model, which you see everywhere, in particular DDPM. Always forget about DDPM, but denoising diffusion probabilistic model, certain variants. And the right is our new kind. So normal diffusion model vector X is a state, and our case is a set. So our state is a set of elements, x1 to xn. So to give an example, if the room is the thing we care about, x1 might be a sequence of coordinates of the first room. And x2 may be the sequence of coordinates for the second room, like this. So that's our representation. And this is the standard kind of diffusion, one step diffusion process. Basically, given xt minus 3, how do we make xt the Gaussian, as you know, with some beta variance scheduling. And this is our case. So black letters are the same as left, orange are the new ones. So left procedure, basically, if you continue doing this, you're going to map everything into zero mean unit variance Gaussian. So we are saying that we're going to change the target. So given in this case, the x0, say it is a basketball player, you're not going to map you to the zero mean Gaussian, something different. So we change the target Gaussian mean variance. And by learning to do so. So again, is an example. So normal diffusion model, say you have this representation, any variable, say 5. When you do diffusion, this can be any value in this Gaussian, zero mean unit variance. And again, every variable the same thing. It's always mapped to the same unit variance. So zero mean unit variance Gaussian. So in our work, we actually do the per element Gaussian. So all the variables which belong to the first element of a set, we somehow learn. You're going to map to this Gaussian with non-zero mean and non-unit variance. That's we learn to kind of predict what should be the mean and variance for the room 1. And then for room 2, all the variables are mapped to another Gaussian. Again, DM says every variable must map to zero mean unit variance, but we learn to change it per element. What can be the Gaussian for the first element? Second element we learn to do. So that's what this formula basically says. We learn to change the target, the mean and variance based on what the data is. Are you basketball players or the Jedi or the computer vision researcher? And we change it for each index of an element. That's what this formula says. And after that, derivation, the standard, this is the standard. Basically, you keep on adding Gaussian. It's the same as adding one big Gaussian, the standard stuff. So we derive the same formula based on our definition, we just derivation. And for normal ODM, there's nothing to learn. Maybe you just manually tweak what's the variance scheduling beta alpha. That's not like a learning usually, just manually pick it. And in our case, we have a learning procedure. What's this mean or the variance the network? So we're going to learn the diffusion process. And based on some loss function, there are a few, but this is a key one. I explain how we are learning this. So again, intuition is, so we have this sample flat plan, and then let's say we run diffusion process. And there's some two networks, which control mu and sigma maps to xt. Then here are all the permutation variants. So we start with all the room. You have n factorial variants. You run the same diffusion model, and then land here. And we basically have a triplet loss. There's xt. Xt is coming from this guy, should be closer to x0 compared to any other ones. So intuitively, we said before, I do not want this two guys to be too close. Because too close, inversion becomes ambiguous. So I don't want them to be closer. So this triplet loss kind of first enforces that this and that should not be too close, separated. And the other one, we want xt to be kind of close to x0. So kind of achieving, if you are a basketball player, I want to find the noise, the Gaussian noise for basketball babies, and Gaussian noise for the vision researcher babies. Kind of has the effect of, if you're coming from this sample, kind of you should be around here and achieve two purposes by the triplet loss. So we learned that. And then denoising is, this is again standard derivation. We just do the derivation mathematically. There's no invention here. Just do this. So denoising procedure have this epsilon theta. This is the standard denoising network, which you train. Then we have all the other one, which we train in the diffusion, the forward part. So the inference time, again, standard. So when you want to sample xt from x0, you basically, the network we learned. So in this example, suppose there are, there are say 7 rooms, and each room, our network gives you what should be the mean and variance of all the variables for say this room. The network gives you mean and variance, and then all the coordinates belonging to the room are initialized by the Gaussian, say this. Then another room gets another mu and the sigma generated by the network. They use that Gaussian to sample. So then we get these things, and then denoise this. So based on the learning network which we learn in the diffusion process, or the network which we learn in the reverse denoising process. So now I want to show you some results. This is for the HD mapping task, ground truth, and result of the state-of-the-art map TR from Tsinghua University. And our results showing animation, denoising procedure here. This is the final one. You actually see correct one, incorrect one in the results, but overall you can see that the geometry is much cleaner, meaning we learn what should be the HD mapping data. This doesn't look like kind of the road vector data, but we learn more higher levels of maybe geometric learning is happening in our case. And more examples, get input views and GT state-of-the-art and our results. And more with animation. Left is GT, right is ours. And we also apply that to floor plan task. Grounded truth, this is the state-of-the-art, this CVPR, because from ETH. And this is the diffusion based. I think this is more autoregressive transformer kind. And another example. And I don't like to talk much about numbers, but for the floor plan task, significantly better than the autoregressive transformer. So this is ETH, this CVPR. We re-engineered to make it even better. Did engineering to make it better. Then this is the result, which is actually pretty big gap in numbers. So autoregressive transformer DM, pretty big gap, although they are highly sophisticated methods already and saturating. And this is the HD mapping results, actually fairly close in terms of the map PR from Tsinghua. Again, we engineered to make it better at the baseline. close for this bench metrics, but for the other one, which really measures the how can I explain? This curve looks like the real gold vector data. Our scores are much better. Let's see. So how am I doing on time? Yes, 23 minutes. So now briefly, I want to mention the arrangement estimation task. This is done by my student Pete, Amin, and Sagar. So the one motivation is we work with a company which makes floor plan using AR application to make a room shape by clicking corners. So the company named the magic plan. But you get the room shape one by one. But user has to manually put them together into a floor plan shape. So room shape one by one can be done by clicking, but how to put them together is manual and very tedious. Can't you automate? That's the motivation. So given the room shape, say 6 rooms, put them together. That's the motivation to do. So the task is you're given all these room shapes. Rotation may not be known, and then doors and windows, and also room types. How can you put them together into this? That's the task. Or in general, there are other communities solving very similar tasks, jigsaw puzzle. Maybe to solve the shattered glass pieces, restore, which may not have too often application, but maybe this really works somehow more like chemical, the protein, even 3D shapes, how these protein fit them together. Maybe some applications on protein, like more chemical studies. So there's some community solving a jigsaw puzzle. So I'll just show you results due to the lack of time. So in short, here we are estimating the pose, which means the positions, X, Y, and rotation, 3 parameters per piece. So again, DM, we initialize the variables, which is the positions and rotation per piece, Gaussian noise. Then use DM to just denoise. So you can see keep on rotating the things. Then solving the jigsaw puzzle, and significantly better than the state of the art, which is usually based on deep learning to find a pair of matches, solve some combinatorial optimization, learning to solve combinatorial optimization to put them together. This is fully end-to-end. You just train one DM dump initialized by the Gaussian, then give you the pose information. So I guess we really made some really big breakthrough for the task. And this is the floor plan generation that works much better than all the related transformers or any other kind we saw. Oh, yes, some numbers, but I out of time, so yes, I'm skipping. So the overall, what I want to convey today is diffusion model can be a really general solver. You have input, output, and DM. You have any solver, put them into DM loop, and adding any input as a condition. And you may have to do something like what we did for reconstruction, but the highly likely you may achieve SOTA performance by having DM. All right, so it has some future challenges, but yes, that's all for today. And thanks again for sticking around and for that attention. Yes, I'm happy to take any questions.
Thanks for the great talk. Why do you think intuitively diffusion model is better than auto-reflexive model?
Yes, a great question. But he's my ex-student. He did all the inverse scans for me. So the one way to think about, which we actually had this intuition for a long time. So auto-regressive transformer, many of the reconstruction paper we did it. So that we can usually do the mask training. We have a GT, sensor data, and then we learn it by say or transformer. Or when you do auto-regressive transformer, you have a GT damage it. Basically removing certain solutions, say 20% of the solution will remove it. Put other condition, then only fill in the missing one. Or maybe damage 80% of the data and learn it. And that's how we typically do for auto-regressive training. So you basically auto-regressive transformer training, you damage data by killing certain entries. You have GT data, you kill these entries, then trying to recover. That's the training procedure. DM is like you gradually add noise and damage. So you're not like killing binary, you're gradually killing by Gaussian noise. And I think, well, DM is also a bit restrictive. You can actually do lots of things. How do you damage? It's a uniform Gaussian, but uniform Gaussian as opposed to killing binary, that's one difference. The other difference is usually auto-regressive transformer, you run only twice or 3 times, like a stacked hourglass. But the DM, you actually do like 1,000 steps. So the amount of augmentation is massive. So you more likely you break down the step into 1,000 steps. So you generate the T equals 632. Then you learn to denoise the 432. As opposed to the AL transformer, you can do binary. So the amount of augmentation is massive. So usually a lot slower to train, but achieve much better in generalization. So that's one intuition that we have. Yes. The other question? Yes.
A very stupid question actually. So, like speaking about conditioning, for example, as like if you have some input, you can embed into this noise space, and it's already stripped and maybe fails. And so my question would be, why is it not enough, and why you need also to learn a sample if you just already moved from there in that embedding space?
But let me understand. So are you referring to particular tasks, say arrangement last because of what?
Can you go like,
Yes, reconstruction.
back to this GDI manifolds and everything?
Yes.
And they were
Maybe around here.
yeah.
Or maybe yes, to be the more picture.
Yes, exactly. A simple go back.
Oh yes, around.
Yeah, this thing. So if we take this as an input, as a like embedding, and we add to this noise, so our this bright spot would be already shifted, maybe scaled. So yeah, now my question: why is it not enough?
Oh yes, that. So for example, we kind of take this for coordinates, and then maybe take the average, add some noise, and instead of learning, initialize the not by Gaussian, but the average of the coordinates here. Is that your question?
Yeah, like whatever embedding or like for image you can do, like I don't know, clip embedding or whatever. Yeah.
No, maybe just not understanding your question. Clip embedding. I see. So you're talking about use clip embedding, somehow get the clip vector for this part of sensor data, use as an initial.
Yes.
Instead of learning the IC. Yeah, that may work, except that the kind of the breaks, we chose this particular formulation, we are still using the Gaussian as a target. Instead of the one Gaussian for the whole thing, for element Gaussian, instead of Gaussian. So still we keep on kind of adding Gaussian noise. So mathematically we can derive lots of things. So a bunch of adding Gaussian noise is equal to one Gaussian. And also you can do techniques to inference time. You can kind of do much faster. Because we share the same mathematical thing, the Gaussian. You change target to be non-Gaussian. I guess it's not about adding Gaussian noise. So we may lose all the benefits we gain from all the other DM techniques, which you're actually using. So interesting, but the somehow I don't know, feel dangerous of not using Gaussian as a target. But maybe interesting. That may work out. We didn't talk about that way. What should be the target distributions?
Thanks for the talk. So I had a question about the kind of conditioning you can use. And I'm particularly thinking about maybe scanning house with my iPhone. Right. And the conditioning basically varies over time because I'm just in this particular corner and I only see blue walls. And then as I move around and explore the space, the conditioning kind of becomes bigger and bigger over time. So what are your thoughts on adapting something like this, where the conditioning is changing, but is kind of consistent across time?
Yes, wonderful question. Indeed. I think that's one big future work. I listed the future work. Basically uncertainty estimation in the whole procedure. I think that's the key. Where was. So in the say, I start scanning the room here. I know where the rooms are, the walls are in this room. When I point here, I already have a pretty good solution for these walls. I don't have a good solution here. So it doesn't make sense to start everything. Everything is Gaussian back to, because it doesn't make sense. These ones I know already. So if you have some uncertainty estimation, this part is still bad. This part is good. We may be able to somehow change how to denoise. Basically, you don't have to go back to a Gaussian for these ones because they have high certainty. For these ones, uncertainties, you have to say go back from the Gaussian or something. That's indeed we're actually doing right now. So something adaptive or more like incremental. And the key is about this uncertainty estimation is, I guess, the key. And if you do that, all inference is going to be fast. You don't have to do it every time from scratch. That's indeed an interesting direction to go. Yes.
So it is a great talk. My question follow up to the first question. So what's the intuition like a PM is a better model for deterministic tasks like reconstruction?
Yes, yes. So maybe again, the deterministic unique answer. So it's really our intuition was this: when you learn the mapping from some input noise to the output, we don't want to learn from this whole thing mapped to a single point. When this is the guidance, that was very difficult. So I think DM is somehow very good for generation, meaning the whole thing should map to the whole thing. So when you learn reconstruction, our trick was, so if you kind of know what is the sensor data, and we have to give it a specific noise to start. If you do that, yes, for many other tasks, the diffusion model is very powerful. So and still maybe not exactly answering, but so you have to be very careful. If you naively formulate whatever the task, unique solution task by DM, you end up doing any Gaussian noise mass map to a single same solution. That's very difficult. So yeah, you have to do that trick. And maybe that's our best intuition so far. Oh, by the way, but again, I don't really understand what's happening. So reconstruction was clear. You have to be very careful of this. But the alignment jigsaw puzzle task, we didn't do any of these. So meaning it's a conditional alignment generation. Condition is a room shape, jigsaw puzzle shape. It just works out of the box. Again, I don't know why. So this specific thing happens for reconstruction. Arrangement, we didn't have to just plug in, boom, 1 week you get this. So we were really like a year trying to do all sorts of transform all together, nothing works. Then 1 week DM, boom, much better. So again, I don't know why for the task, somehow it just works. Somehow we have to do something special. So still we don't know why.
I have a question towards the limits of this course application. I think here the demo shows like most of the vectors are fairly straightforward. Is it because this application or there's a limit that you cannot go upon like more complicated?
So complicated, for example, say the entire building being model.
Yeah.
Or I guess the lack of data. So data, yes. There's very little. There's some efforts, but usually whenever we want to do something full 3D house model, not the floor plan, there's no data. So we cannot do this. So lack of data through 3D complexity is really suffering. Especially if you go to 3D, you need maybe more data, but more difficult to annotate. And maybe company has it, but we cannot access as the academic person. So I think that's the biggest challenge, that data.
I actually have a question follow up the previous. With your examples on like the Jedi example, it was like really clear on what's happening. But going back to this specific task of floor plan generation, I understand why practically having samples coming from different Gaussians would work and prevent mode collapse or like stuff like that. But like especially with the structured 3D data set, and as far as I understood, like your prior there is basically the semantic room type. A lot of rooms are pretty much similar, like rectangles, just the size might be different. And like given that data is syntactically generated, assuming that they're coming from the same range of size and stuff like that, again, practically it makes sense of why we need different multiple Gaussians. But I'm having a hard time understanding why theoretically do we need multiple Gaussians.
By the way, so the multiple Gaussian thing is only for reconstruction.
Yeah.
The generation we didn't have to do.
Yeah.
Everything is
that for
reconstruction. I see. But again, so the question was, I thought you were talking about generation, but reconstruction.
So for reconstruction, I understand that like for practically to prevent all the issues that came up.
Yeah.
Why do we need different Gaussians?
I see.
Design like the rooms, but like
Yes.
there's actually not a lot of semantics in those.
Yes.
Right?
Yes. Well, the one easy way to understand is suppose I am reconstructing let's see, three room. Then so I have like a 3 kind of vector to initialize. So if three vectors are all initialized here, they're looking at the sensor data, there's room. So trying to noise that guy to be the room in front of me, sensor data. So if you, the non-max suppression, or basically there's another guy trying to explain the sensor data, so I should move to another sensor data. This one doesn't happen somehow, effectively. Which is also similar to, I guess, maybe non-max suppression. So the DET, if you go to the detection task. So they say that transformer DETL seems to understand non-max suppression effectively. So there are like a multiple, like in DETL case, you make dominoes, trying to detect objects. So trying not to have multiple domino detect the same object. So they learn to somehow avoid collisions of detection. But somehow that doesn't work well. If there are three kind of the vector data node, if there's one room in front of it, everybody trying to explain that, although there are two rooms here, but nobody's trying to go there. If you initialize everything uniformly, you can get stuck in local minima in a sense. So that's one intuition, maybe to explain.
Yeah, thank you. Are there any other questions? How much?
Yeah, thank you.
Very nice talk. Great, thank you all. That's a wrap. For attending. Thank you so much for joining.
Yeah, thanks.
Appreciate it.
You are at the Zillow. Yeah, you work at the Zillow.